very good morning to one and all. I, Ganesh Pai, welcome you all to the third day of online short-term training program on machine learning for societal applications. I hereby take this opportunity to introduce the speaker of the morning session, Dr. P. Shivakumara. Dr. Shivakumara completed his BSc in Computer Science from University of Mysore in the year 1996, B.Ed from Bangalore University in 1997, MSc in Computer Science in 1999 from University of Mysore, MSc Technology in Computer Science from University of Mysore in 2001, and PhD in Computer Science from University of Mysore in 2004. He served as assistant professor from 2004 to 2005 in APS College of Engineering, Bangalore, as a research fellow in School of Computing, National University of Singapore from 2005 to 2007 and 2008 to 2013, as a research consultant in School of Computing, Computer Engineering, Division of Computing Systems, Nanyang Technological University, Singapore from 2007 to 2008. He served as a visiting senior lecturer from 2013 to 2016, as a senior lecturer from 2016 to 2019, and presently as an associate professor in Faculty of Computer Systems and Information Technology, University of Malaya, Malaysia. His broad areas of research interest includes video text detection and recognition, fraud document analysis, forgery detection, document images, forged handwriting detection. He has 99 journal publications and 171 conference publications at his credit. He has written one book and five book chapters. He has 3,514 citations with H index of 30 and I10 index of 75. He has guided two master's students, completed two projects, one consultancy project, and seven active collaborations. Three PhD students have received the doctorate under his guidance, and two are currently pursuing. He is a research consultant to MIMOS Kuala Lumpur, Malaysia, on license plate recognition from 2nd January 2015 to 2nd January 2017. He is a visiting scientist at University Technology Sydney, Australia, Maharaja Research Foundation, affiliated to Mysore University of Mysore, Computer Vision and Pattern Recognition Unit, Indian Statistical Institute, Kolkata, India, National Key Lab for Novel Software Technology, Nanjing University, Nanjing, China. He has received 13 research funding projects from 2013 to 2020, from most of them from Malaysia and China, with grants up to 1,29,400 ringgits and 40,000 renminbi respectively. He is a reviewer for 44 international highly reputed journals or letters such as Applied Soft Computing, Pattern Recognition Letters, IEEE Transaction on Emerging Topics in Computational Intelligence, Malaysian Journal of Computer Science, IEEE Transactions on Image Processing, International Journal of Imaging, to name a few. He is a guest editor for a special issue on machine learning in pattern analysis, Springer Nature of Computer Science. He is an associate editor for journals such as Pattern Recognition, CAAI, Transactions on Intelligence in Technology, SN Computer Science, ACM Transactions on Asian Low Resource Language Information Processing, Malaysian Journal of Computer Science. He has received Dynamic Indian of the Millennium Award by KG Foundation, KG Hospital, Coimbatore, Tamil Nadu in 2017, Top Reviewer Recognition Award in Pattern Recognition Letters in 2014, Outstanding Reviewer Award in Computer Vision and Image Understanding and Pattern Recognition in 2019, and Outstanding Reviewer in IEEE Transactions on Multimedia in 2020. He is an assessor for promotion application at Monash University, Malaysia. He has conducted more than 10 international and national and international workshops. He has been program committee member for 19 and reviewer for 33 international conferences and workshops. He has chaired 20 international conferences at different roles and has been the keynote speaker for 9 international conferences and symposiums. He has delivered more than 30 invited talks and has been the examiner for more than 10 PhD theses. He is an associate member for IEEE and a life member of Indian Unit for Pattern Recognition and Artificial Intelligence Association. With this short introduction, I welcome Dr. Shivakumara sir for the program. Welcome, sir.
Yes. Okay. Thank you very much.
Without further delay, I request Dr. Shivakumara sir to start the session. Over to you, sir.
Oh, okay. Thank you. Thank you. Sure. Sure. I will take it. No, no issue. Okay. Anyway, thank you very much, madam, for giving this opportunity. Okay. Now, fine. This is the topic. Okay. Text detection in the 3D video images. So maybe just look at the title now. It is not just an text detection in 2D images or something else. Now you just try to understand what is the difference between a 2D images, and of course there is a one more topic in our field, text detection in natural scene images. So now, yeah, you need to understand that how 3D video is different from natural scene images and 2D images. Yeah, then it will be interesting topic. That is where this topic is something different. Okay, so natural scene images, yes, you can expect even 3D also, 2D also, but most of the work, yeah, you can look at the literature survey. Most of the work focus on natural scene images. That means in text detection in natural scene images. Natural scene images, maybe you can take example like in a building name, street name, or anything, something text with the scene information, scene as a background. Then we can say natural scene images. So video is something different. It is not actual natural scene images. So video is always you go with a video, and from the video we will try to extract an individual frames. So we just call it frames, not like in images. So maybe still images, or maybe still frames also, we can say still frames also. So my point is this one: how natural scene images are different from video images. Then I will try to explain how 2D is different from 3D. Okay, so when you are addressing 3D images, 3D video images, yes, there are many complexities here. There are many challenges. It is not so easy, and it is not something like simple to process the things so or achieve the result. So in that way, just I'm trying to make you understand in what way 3D video is different, and in what way it makes difference, in what way it makes any sense. Okay, so yeah, natural scene images, yes, the name indicates here the natural scene. The word itself says there will be a background scenery. Okay, that is a natural scene images. But video, yes, it is a video. Of course, definitely video means one can expect any video information here, temporal frames generally. So we, of course, in my work, we don't consider temporal. Of course, we consider temporal frames, not in the first work or second work. Maybe third work, we will consider temporal frames. Of course, in case of video, there will be extra information. So temporal time information. So number of frames per second. So how we can utilize, how we can explore this temporal information for achieving good result or better results for video images. That is the point here. That means in case of still frames or individual images like in natural scene images, we don't have a time parameter here. That means we don't have a temporal information. So that is where it is a difference here. That means video will have, since you have a temporal information, definitely it will be extra information and additional information for you to tackle some problems, especially occlusion, especially low contrast. Suddenly suddenly something will disappear, suddenly we can see something zoom in, zoom out. Yeah, there are so many issues in the video, especially when you take tracing and tracking. So in this case, of course, unless you have a temporal information, unless you trace the things, and unless you see some extra information, it is not so easy to detect or recognize or trace anything. So in that way, video is always complex. So tracing, tracking, recognition, detection in video. Of course, there will be extra temporal information because of the motion, because of the temporal information. Definitely one can solve the problem. But when it comes to natural scene images, 2D images or natural scene images, yes, we don't have that information. So we don't have a time information. So more or less background and complexities are same. Maybe perspective distortions, text orientation, low contrast, high contrast, or maybe background variations, foreground variations, so arbitrary shape. Like this, we can expect in the same kind of a complexity when you compare with both the natural scene and video. But when it comes to time parameter, temporal frames, yes, the video provide extra information for you. So in that way, natural scene and video, yeah, there is a difference. But what is the difference between 2D and 3D here? Yeah, definitely in terms of when you look at text detection point of view, yeah, what is the difference between 2D and 3D images? So 2D, yes, it is of course just in a plain images X and Y. 3D images, since you will have the extra Z information, that means depth information will have. So because of the depth information, what will happen to what is the effect of this 3D on text? That is a point here. I'm not dealing in a 3D information or a 3D reconstruction or yeah, that's not my job here. Just I'm trying to look at what will happen to the text. If it is a 3D, if it is a 2D, then what is the difference here? Just I'm looking at in a complexity or looking at in a text information here. So if it is a 3D, so what happens? So 3D text, how we can say it is a 3D text from our eyes? So from our naked eyes, how we can understand that that is a 3D text? Of course, when you capture from the orthogonal direction, that means in a direct straight head, then even there is a 3D in the image, we cannot visualize, we cannot understand there is a 3D because you are capturing straight away. So we cannot see the depth information. So that means you are trying to capture the same text in different angle. So when you take when you capture in different angle, then we can see some kind of an orientation, especially we call actually perspective distortion. So not only that one, we can see some shadow information. So in case of 2D, we don't get a shadow information, but in 3D, there will be a shadow. This shadow is actually creating problem for us. And depth information, because of the depth information, what happens, generally in case of a 3D video and 3D images, especially movie and sports or something you just can observe. So there will be, we are trying to decorate the characters. We are trying to write in different form, different way, not only just line, even individual character also, we can see individual character, the shape changes, the color changes, so many changes will be there. That means they try to draw attention, so they try to attract, so with some different writing styles and yeah, so many forms. So that is actually the problem for us. In case of 2D, since you don't have a depth information, it will be something like in a plane. So it is easy compared to 3D. So what we expect in 3D, definitely there will be a shadow and perspective distortion. That is another thing. And one more thing is decoration. So that means you are trying to decorate the characters. So maybe third case of an English alphabets. I think nobody knows that one. If someone write and use in a third case, probably yes, it's very difficult for us to understand what is that character because we don't practice that one. We don't use that one. Exactly the same here. When you write decorative character, what happens? That character will overlap with the actual character. And shadow, what is the problem with the shadow here? Since when shadow is present, definitely we can see uniform pixels here. Shadow will have a uniform pixels, like in same color values. Now the problem is, since shadow is connected to text information, so now the whole connected component character becomes something different now. For us, it is okay. We can easily differentiate what is shadow and what is character here. But when shadow connected to character and text information, then it becomes something totally different. For us, it is fine, but for algorithm, how it can differentiate where is shadow and shadow boundary and text boundary. So that is actually very difficult. So what I'm saying here, because of the shadow, that means in the presence of shadow and decoration, decorative characters, so making this problem very complex. Okay. Now how we can solve the problem? That is the whole story of text reduction in 3D video images. Okay. Now, this is what actually I think Madam and even Shekhar sir also we discussed what should be the topic for this session. So yes, I think you already got information. What should be the first session, what should be the second session or third session, whatever it may be. There will be two sessions in my cases. So first session, I don't know how much time it will take. Anyway, you just will go with your own timings. How we can solve this problem? Number one, classification of 2D and 3D video images. See, what is our ultimate goal? Ultimate goal is somehow we need to achieve better results. Whether it is 2D or 3D, whatever it may be, so our target, our aim is to solve the problem and achieve the result. So here, how we can solve the 3D video text detection problem? So there is one way, classification of 2D and 3D images. So maybe just you think like this, there is a full and then there is a folder here. So in which we can see 2D also, 3D images also, video also, so many things are there. Even one image, single image can contain 2D text also, 3D text also. Like this, you have a mixed images now. So when you have a mixed images, so there is a problem now. Because see, 2D image contains 2D text, 3D image contains in a 3D as well as a 2D text. Now, when you have a different nature, when you have an image with a different nature and different complexity, then it is not so easy to develop an algorithm now. If it is just uniform and plain, then just there are no variations at all, then it is very easy to develop an algorithm. When you have a large variations, like in variations in the two text information, appearance, so many things, then it is not so easy to develop an algorithm. So what I am saying here, so if you want to solve 3D problem, then there is a one more way. Let us classify 2D and 3D video images now. So we can classify, because see, as I mentioned earlier, there are a lot of methods and many methods have been developed for 2D text detection, especially in natural scene images. So when you give a 3D images as input to those algorithms, then probably you cannot expect the same accuracy. Definitely there will be some poor results and there will be a poor performance. Definitely, no doubt in that, because you're not trained your algorithm or your model with 3D images or 3D text information. So it is impossible for you to achieve the same result. So anyway, my question is this. So how we can solve the problem? Can we modify the developed algorithm for applying on 3D? That is one way. Or can we classify 2D and 3D so that automatically we can use existing algorithm for text detection? This is my point. So initially, of course, when you see the problem, generally what we do, you always think in a different ways of solving the problem. That is what in our researcher mind. Yeah, that's what always we think. Same problem, but we split into so many things. And definitely for same issues, we'll try to think in different ways of ways to solve the problem. Now, I'm thinking when I started working on this problem, of course, I tell you why we started this problem. Maybe I'll come back to that introduction part. So later, so I think soon you will see 3D TV. That means you will watch 3D movie and news, everything in your home. So that means whatever you have a smart TV and everything, it will be replaced by 3D TV. Yeah, that's what I think research group is working on that. Or maybe I think, I don't know, Samsung company or some company will release 3D video, 3D TV. So definitely it will come. But of course, no need to wear spec in spec. If you want to watch 3D or 4D movie, you have to wear a special effect, spec with a special effect. Yes, which is not necessary. So just from your eyes and how you are watching 2D TV now, like this, similarly, we can watch 3D TV. So it will come soon. So that is what our target now. That is actually the applications here. That means one day you can see 3D images, 3D TV. So then how we can understand the content in the 3D video. So that is the point here. So anyway, I'll come back to that point. Now you just try to understand the flow, what I'm going to discuss today. So classification of 2D and 3D video images. That means how we can solve the problem. So one way is to classify 2D and 3D. So if you classify 2D and 3D, then we can use existing algorithms of 2D for solving 2D problem. So 3D, of course, there are no algorithms. So now, yes, you can develop your own algorithm now. So when you have a both 2D and 3D, then it is very difficult. That means complexity increases now. Complexity is very high. When you have a complexity is high, it is very tough for you to develop a generalized method. So if you classify 2D and 3D, then it will be easy. Now you're focusing only on 3D, not mixing, not focusing on targeting, not on both 2D and 3D. Just you are targeting only 3D, and you're just targeting only 2D now. So then the problem is simple now. So when you mix both 2D and 3D, then problem will be complex now. So like this, you can reduce the complexity. How we can reduce the complexity? Through classification or by classification now. That is the first part, okay? So after classifying 2D and 3D images, next we did one more work. We have done one more work on classification of 2D and 3D text in the image. That means we classify images. That means a full image. We take a full image as input then to classify. So after classifying images, then yes, there will be text information in the image now. So we'll try to again classify 2D text and 3D text, not the full image. That is the second work. Okay. Third work, as I mentioned, yes, why don't we develop unified or single algorithm which can detect both 2D and 3D text information in the image. That is our target. Okay. So, and finally, yes, there are some research issues. So probably, yes, if you have a time, and yeah, we'll try to discuss those research issues. So that is the last topic. And initially, let us finish in one by one. So classification of 2D and 3D video images first, and the classification of 2D and 3D text. You just, there is a difference here. So first problem, we are trying to classify the whole image. Second problem, we are trying to classify the text information. And finally, we are trying to develop a one method. So this is a one flow. Okay, how we can solve the 3D text detection problem. Okay, of course I'm not touching recognition problem, just I'm discussing here only detection part. So after detection there will be one more step, recognition part. Okay, so maybe that will be the next topic. So at present, in this session we'll try to cover, yeah, these three topics along with um, future research issues. Okay, introduction. I think I've already given many things now. So introduction is very simple here. Yeah, text detection recognition. Where can be used? Where can we use this text detection recognition? Of course, now I think very popular. Everyone knows in the world now. Self-driving vehicle, or that means automatic driving vehicle without pilot. That's what in everywhere is happening now throughout the world. I think many companies are developing algorithm working on automatic vehicle driving. So autonomous automatical vehicle driving. So of course, how it is nothing. Of course, we need a text detection part here. So license plate detection, text detection part. So there will be camera on your car or something. Camera will be mounted on your car. So automatically it will, yeah, maybe assume that it will rotate 360 degree, rotate by 360 degree. So automatically it will capture, okay, left and right and top and all information now. So when there is a vehicle, so yeah, behind also, in front of, rear end, and the, behind also, automatically, yeah, it can detect, oh, there is a license plate and there is a vehicle here. And of course left and right side, probably you can see street name, this name, that name. So like this, there will be text always play very important role in this project. That means, automatic driving vehicle, that is a very simple applications here. Of course, that is an emerging application now, so many people are working on that. So yeah, like this, there are many applications. I don't want to touch on those applications now. So of course, even we can say that now nowadays, I think in one mobile, yeah, maybe, I think, I don't know, you have an experience, you might have an experience or not. If you go to Japan or China, so definitely every mobile will have an inbuilt function, recognition function. That means recognition algorithm. When you talk in English, automatically they will have their own software in mobile. So they will translate. You talk English, you talk in English, automatically they will receive the Chinese language. So because it's very difficult to communicate with the taxi guys and the local people in China and Japan. So in Japan and China, if you go to any supermarket, any market, or wherever, so I think every mobile will have an inbuilt function like this system. So similarly, when you write something, automatically it will translate to Chinese, Japanese. So even taxi guy, you just write in English, automatically you will receive, automatically you will get in a Chinese language. You can, so that you can understand. So that means what I am saying here. So when foreigner comes to India, how we can communicate, how we can understand. So it is something like in recognition. Okay, you need to recognize English. That means he has to recognize English to translate to, or recognize local language to translate to English. So that is another application here. So like this, we can find a lot of applications. Even sometimes we can think uh, social media also. Now, of course, if you don't touch applications of social media, then people won't appreciate your work. When you're writing a paper, when you're publishing a journal or something, yes, you need to connect latest application, so recent application, emerging application. If you don't touch social media application, then people again think that the reviewer or reader or think that, oh, what is the use of this work? Because that is a trend now. That is a trend now. So of course, in our case, we can justify in this way. So let us assume that there will be a lot of videos or uploading, images are uploading on social media. Now, can we say it is a forged video or fraud document or something else? How we can say? Yes, for that actually we are thinking, and we are, of course, we have been working on that. So assume that like this, and there is one case now. There is a video. He changed in a little bit the content of the video, but not the text. So now our text algorithm, text detection algorithm or text detection or recognition algorithm automatically detect the information and recognize the information now. So that means text gives some meaning now, but assume that there is an algorithm which gives the meaning of the content. So now, since it is a forged video, yeah, content gives a different meaning now, but text gives exact meaning now. So what we can say now, oh, text is giving different meaning, but content is giving again different meaning. So there is a mismatch now because it is an image. So of course, whatever we write on the text, whatever we write a text on the image, that should give a same meaning of content of the video or images. So if there is a difference now because of the change in the content, because the guy changed the content in the video, because it is a forged video, fake video, but he did not change the text information now. So now text is giving actual meaning, but content is not giving actual meaning now because of the forgery. So like this, we can expect, we can justify our application. Of course, for your problem, unless you find a new application, it is very difficult for you to survive. Of course, not survive in the sense what publishing paper is very tough, especially top journal. So yeah, this is the way. So now I am saying that, okay, yes, our text detection can be used even for social media also. So automatic driving vehicle also, because these are all new applications and new trend. So now I need to touch, I need to connect how my problem is useful in different, especially new applications or recent applications. So that is a point here. So okay, now I think I've already mentioned what is the difference between natural scene and video images. So yeah, video. Another point I think I forgot. Video always will have two kinds of text. See, one is a graphics text, another one scene text. So graphics text is nothing but a what? Edited text. That means subtitles, right? Maybe when you are watching video, watching your news, so you can see subtitles. So news video, news channel, or when you are watching a news channel, so you can see subtitles. Those we call graphics text, superimposed text, artificial text. Yeah, there are different names. But another text will be there, scene text. See, this is actually graphics text because this is actually subtitles. Okay, we are see edited by the person now. So over the video. Now this is actually scene text. So in case of video, we can expect in both the text, not just in a graphics text. We can expect even a scene text also. That is another problem here. That means video can contain two kinds of text. So graphics and scene text. What is scene text actually? Part of the image, like in a building name, street name, or any name which is part of the image. Graphics text, this is something edited text. Okay, so there will be two kinds of text. Look at the definition now. Edited text, natural text, scene text. So that means scene text, we don't know nature of the scene text. It can have a low contrast, it can have a high contrast, it can be orientation, it can have a orientation, different things, because we don't know that one. It all depends on the context and the image. But graphics text, since it is a edited text, why it is edited? Because we have to read. So if you want to read, of course, you should write properly, you should write legibly, you should write neatly. Okay, that means easily we can differentiate now. Graphics text definitely will have a high clarity, high contrast, visibility, everything is good. But scene text, no. It can be anything now, because we don't know. We cannot predict the nature of the text. So what I'm saying here, so video will have two kinds of text. So when you have a two kinds and text with a different nature, then again one more problem now. It is not so easy to propose algorithm which can detect both the text. It is difficult now. So that is another complexity of the additional complexity of the problem, video. Okay, so yeah, these are all effect. Of course, these are all quite common for natural scene images. Even yeah, the video and natural scene images share all these causes and problems. But except video contains yeah, both caption and scene text, or graphics text and scene text. But natural scene images contains only one kind of text, that is scene text, not graphics text. Okay, in that way it is a different. Now look at some sample images. There are so many images here, scene text, and yeah, a lot of difficulties and a lot of challenges here. So this is a 3D text. Look at now. So 3D, we can expect some shadow also, and some kind of decorations also, and decorative characters also, like. So this make problem more challenging. Okay. Yeah, there are some other challenges also when your folder or something and includes, so this is actually captured from a different angle. So multi views, that means the same spot captured by different angle, so different side also. So one left side, right side, like this. Of course, there is a spot, same spot captured in different directions. Okay, so that is a multi-view. That is another problem. And again, one more problem because of the occlusion also. Sometimes you can see some kind of an obstacles like this. So due to this tree, and we cannot read characters properly. So that is another problem due to this grid and other things. Again, it is a problem here. So like this occlusion is also another problem. And another issue here, actually aerial images. That means when you capture from the drone, that is again it will be another problem now, another challenge now. So this is totally different from orthogonal okay, images captured by orthogonal direction, straight head direction. Okay, now you are capturing from the top. So when you're capturing from the top, then of course the information given by image is something totally different now. So straight head is different, capturing top information is different now. So when you're capturing the top information, you don't see this license plate at all. So where is the text here? Because you are capturing from the top now. So you are just getting information of the surface of the car body or something, not really license plate. So in that case, actually, really it is a tough and challenging problem for locating license plate information in drone images. Okay. Now, anyway, that is not our topic now. Just highlighted what are the challenges in the text reduction part. So when you capture by drones, what will happen when you capture in a different angles and different directions? What will happen? So that was just I'm trying to show. So how text reduction um, difficult in different scenario and different cases. Okay. Now this is actually our problem now. So 3D images. So as I mentioned here, look at this one. So it is not so easy to detect. See, we don't know what kind of a shape of this character, and look at this decorative, characters in written in a different form and different way, and look at the shadow information here. So for us, it looks very good and attractive and something in attention also. But when it comes to developing a method, yes, it is not so easy. Okay. Yeah, there are a lot of methods developed. Of course, so text reduction is a very mm, what I can say emerging topic. Many people are working on that, and it's a very interesting topic for many people. So every day you can see new paper on this topic. Every day you can see one or other way people publishing a paper on this. That means what? There is a lot of scope for this, and there are many challenges. Not only challenges, so there are a lot of applications for this. So that is a way. Okay. So now, of course, actually, it is a field of document analysis. So document analysis people started working on video text detection and recognition. So now, yes, of course, I don't want to explain too many things about a literature survey here. Just I will try to highlight document analysis methods. Definitely not not suitable for this one, because I think very well document analysis means immediately we can think the plain background. So like document writing, white paper. So of course, so when you develop algorithm for plain document, how you can expect a complex background image, like in video and scene images, that is impossible. So that is a problem with document analysis. Of course, there are natural scene text reduction methods are there. Yes, these methods, as I mentioned earlier, yes, video contains two kinds of text information. So yeah, then these methods probably may not work, probably fail to achieve better results for 3D images, not only 3D video images. Okay. So video text detection recognition, of course, there are many methods for video text detection recognition also, but again, there are some issues with those methods. Now I think new trend is deep learning. So I think for every problem now every researcher is thinking how to apply deep learning techniques to solve the problem, because just now this is the new trend now. So without deep learning concept in your paper, I don't think you can publish a paper. So it's now for all the papers deep learning is must now. Of course, whether it solve the problem or not, that is different story. But if you want to really publish a paper, yes, you need to add element of deep learning. Otherwise, it's a very tough job for you to justify. It is very simple question. If you propose even novel method or good model or anything, assume that even you got a very good result for your problem, but just the reviewer ask only one question. Now, trend is developing a or proposing a deep learning based model or architectures. So why you did not compare with the deep learning model, deep learning architectures? Why you did not? So then how do you ensure that your method is better than deep learning models? Because everyone knows that deep learning model are always powerful and give very good result. So when you have this kind of things, and how do you ensure that your method is really better than a deep learning model? So we cannot answer. Yes, though you got you proposed a very novel method and you got very good result, you solved very complex problem, but still it is tough job if you don't include compared study with deep learning model. Okay. So anyway, for me, because I am not a machine learning guy and even deep learning guy, so I cannot comment on deep learning things. But what I can say here, for me, deep learning based methods have their own limitations and their own problems, especially when it comes to generalization ability. So generalization is not possible because you are training with a predefined samples. So when you train your classifier or with a predefined samples, then how you can expect it will work for unknown sample. So it's always the question, question will be there. So so that means it is very simple. So these methods, yes, definitely give very good result, very good accuracy, but accuracy depends on number of samples that you choose. So if samples does not include your unknown sample, what you are giving as input or testing sample, yeah, then finish. Then you cannot expect any good result. So that is what the limitation here. So I cannot say it is a robust. Of course, we can keep training. That's the reason they go for a large data. Why? Because whatever you choose a problem, that should be included in your training sample. That is the way. That is the reason they're trying to extract and trying to have a more number of images and a large number of images. Why? Because whatever you consider a problem, that should be included in the data set, in the sample. So that is the way they are going, that is the way they are trying to learn their classifier and a model or train their model. Okay. Now the main problem is, can we develop a generalized method? Okay, so that's the thing. So these are all, of course, for me, in case of 3D video, you should remember here shadow and decorative character. These two make problem something different compared to natural scene text reduction and 2D text reduction. Okay, so now our job is to solve the problem. Yeah, this is actually just we got an acceptance, so it's not even presented. So it's ICPR conference. We just got result acceptance, and yeah, we have to present this paper, I think, in next month. Next month we have a schedule. It's an online conference. This is ICPR, International Conference on Pattern Recognition. So we proposed a concept of local gradient difference features for classification of 2D and 3D natural scene text images. Okay, see here, as I mentioned earlier, first how we can solve the problem. One way is to classify the images. When you classify the images, then we can focus. That means indirectly we are trying to reduce the complexity of the problem. When you mix it both 2D and 3D, then it is very difficult for you to develop an algorithm. Of course you can develop, but we are not sure, yes, we can get a good result, because 2D and 3D have different natures. Okay, when you classify 2D and 3D, then it is easy. Then we can focus only one problem, not two problem. So when you classify 3D, then you focus only 3D. Don't forget 2D here. And of course, as I mentioned earlier, for 2D, there are a lot of algorithms are there. Why again you are solving the problem? Again, you are developing one more algorithm which works for 2D, not necessary. So in that way, classification helps here. So you just classify 2D and 3D. So how we can classify 2D and 3D? That is a question mark. That is the idea. That is a whole work here. Okay, what is the motivation here? You look at this one. This is actually 3D images now. So we have just run on PSC net, that is actually existing method. There's one network on one architecture, that is existing method. So deep learning based method. So we just tested this method on 3D images now. Okay, so now this is actually 3D. This is 2D. Now what is happening now? For this, yes, we are getting some result. For this, yes, we are not getting the result. For this, yes, we got some yes result for this one, but for this, yes, no. That means what? Yes, this algorithm, because this algorithm is developed for 2D, not for 3D. So we miss, this algorithm misses this text information now. So that is what the problem here. That means what we are showing here, yes, whatever we have developed and so far, those methods may not work for 3D. Okay. Similarly, so now this one you see text reduction by method and 2D after classification. This is before classification. After classification means we have classified now. So definitely now this is a 2D. This algorithm is developed for 2D. Definitely it gives good result for this one. For this one, what we did, we can tune now. We can change the parameter now, or we can train your classifier now with the 3D images now. Okay, because you classified now. Same algorithm can be tuned, trained now with the 3D samples. So see, after classification, what happens? Same algorithm is giving better result now. This is what advantage of in classification of 2D and 3D images. Of course, what you have to think here, what you have to understand here, not like in showing the results or something. You need to understand that okay, this is one way of in class solving the problem. So there is a 3D, of course, that is a whole approach, whole problem. That's a big problem. 3D video text reduction and recognition, that will be the big problem now. So now we can split and we can solve in this way. Okay, this is the one way of in solving the problem. This one way of in proposing our own methodology. Okay. So what is local gradient difference? You see, this is a one simple approach based on the gradient information. This is a one window here. Okay. So of course, 3 by 3 window, and within that we can see some pixel values here. Now, so it's a gradient window means what? It's a gradient values. Okay, we have a gradient values. So let us say some values in a 3 by 3 window. Now the difference is something like this. This is center point, and just subtract with the neighbor elements. Subtract neighbor elements with centroid. That means absolute. So you are getting some value. Okay, so sum. So you are replacing that value. Okay, center value is replaced by this one. Like this for every value, we get a new value here. Okay, again this should be the input for this one now. Now use this one, apply same operation, you get this one. See what we are doing here. I think you know very well what is a gradient. Okay, what is our goal here? We need to classify 2D and 3D images. So what do you want now? How we can classify 2D and 3D images now? That is a question mark here. See, in case of 2D, what happens? Of course, there will be, let us say gradient is nothing but a what? Gradient is nothing but a what? Edges now. In case of 2D, yes, you can see some edges of the text information. In case of 3D, what happens? Because of the shadow, you will have any extra edge information now. See what we are doing here, gradient window. So this is a gradient information. This is one more gradient. This is actually another gradient now. So that means improved version of this one, improved version of this one. So that means we are trying to filter, trying to get vital information, important information. That means we are trying to remove and suppress something to get new information and better information now. See for the same pixels, 2 is here, 8 is here, 40 here. That means you are trying to enhance the pixel information or trying to extract the information which is very important for us. Okay, so that is the reason we are saying in a candidate pixel detection. So that means we are trying to candidate pixel means it should be representative of the text information. It should not be representative of non-text information, because you know very well that text will have any edges. Non-text or maybe background information may not have any sharp edges like in text edges. So gradient is always representing, let us say, edge information now. So we are trying to extract any edge information in different way now. Of course, all edge information is not necessary. So we are focusing particular edge information which represent the text. Okay, edge which represent the text information. So this is what the information. Just look at this in our sample result here. See the absolute gradient images. That means this for input images, for each input images, actually 2D and 3D. For each input images, we are just we obtain absolute gradient images. See gradient, you look at the gradient, always you can see some kind of a sharpness and a brightness at edge pixels. That is nothing but about a gradient. So that is the output of a gradient. So gradient always suppress background information to highlight edge information or sharpen edge information. Okay. Now look at this. What is the interesting point for me? Look at the interesting point. It says look at 3D text. 3D text will have an additional edge information now. You got an additional edge now. But here, not like this. See, text is a normal text now. But because of the 3D, because of the shadow, you are getting extra edges here. That is observation here. Now, how I can extract that information? Now, with the gradient information, definitely we can expect this is something like a high information for me compared to background. Of course, there are high information of non-text also. But anyway, this high information includes text information, and it does not include background information. And so that means indirectly what you are doing here, you are trying to reduce complexity step by step. Gradually you are trying to reduce complexity of the problem. Okay, now, so what we did here, dominant pixel detection by max-min clustering. See, as I mentioned here, so these values, wherever you see the brightness, so we can expect in high values. Wherever the background is dark, we can expect in low values now. How I can classify these pixels are bright pixels? How we can classify bright pixels and non-bright pixels? How we can classify? So for this, just we used in a simple max-min clustering algorithm. What is max-min clustering algorithm here? So let us say, so you are trying to choose a max element here, that's a maximum element in the matrix. Let us say this is one matrix and then a gradient values. This is a gradient values. You have it is nothing but a matrix for you. You just try to choose the maximum element. What is the maximum value and what is the minimum value? Okay, so now you have it says a two class problem. Now you have a maximum element and a minimum element now. So you just take in values of the pixels or gradient values and compare with these two max and min element now. Okay, now the value, the gradient value is near to max, you classify it as a max cluster. If it is near to low, that means in min, you classify it as a min cluster. That means what is our expectation here? Since edges representing edges marked by brightness and highlighted by brightness will have a high values. So that will go to the max cluster. The values which are dark go to min cluster now. So that is what actually these are all actually max cluster of the result here. So that means you can see clearly now. So all edges, especially the text edges, even the non-background edges, that means we have removed some of the unwanted information, background information. So what we can say, now you reduce the complexity now. So input image will have in a complex background and so many information is there, which is not required now. So we are trying to get in a dominant information now. Okay. So these are, I just defined dominant pixel, defined as a dominant pixels now. Okay. Now I am trying to apply for each dominant pixels. We are trying to compute local gradient difference as I mentioned earlier. So that means again, I'm trying to tune, I'm trying to eliminate some of the pixels because I want particular pixels which represent the text information. I don't want in all the information now. So that is the reason, again, I am applying one more step here, local gradient difference now. Okay, this is a gradient image. From the gradient image, we got some dominant pixels now. From the dominant pixels, we are trying to get candidate pixels now. So that means we are trying to apply a local gradient difference to detect candidate pixels from the dominant pixels. That means what? Dominant pixels, that is the input. Dominant pixels already removed some of the information now. Again, out of dominant pixels, we are trying to remove some of the false dominant pixels, false text pixels. Yeah, this is the final result of a local gradient difference here. So now what we did actually, again, we applied employed k-means clustering here. See, for every dominant pixels, we got some information. Of course, for every dominant pixels, we calculated a local gradient difference now that gives some values. Again, it should be high value for the text information, low values for non-text information now. Now see, k-means clustering, I think you know very well, it is also clustering algorithm. K equal to 2 here. It is exactly work like a max-min clustering, what I explained earlier. So k means k equal to 2 here. So automatically it gives in a 2 clusters now. So these are actually max cluster of the result here. Look at this one. Almost we have removed in a background information. We just retain. That means in a k-means clustering give only text information. Along with the text, there are some noise information here. But here, look at now. Same thing is true for 3D also. But what we can observe here? You try to observe here. So see, always you try to remember here. So whatever we get a result here, you just keep in your mind how we can differentiate 2D and 3D. That should be there in your mind now. That is what our goal also. So to classify 2D and 3D, we are doing all these steps. Okay. Now you just remember here. Now look at the information and information here and information here now. So what is the observation here? What is the difference here? This is also text. This is also text. But there is a difference here. What is the difference here? Look at the text information. All pixels like in clustered pixels now. Look like a clustered pixels now. So, but here, look, there is a text information, but we lost information here. Even we cannot read the text here. But here we can read. That means all pixels are preserved, and look like a dense and cluster now. But here we are losing. So that's what we call, sometimes we can in sparse representation. So that means we are losing information here. So that means pixels are scattered here. Pixels are grouped here. Pixels are scattered here. So this is observation here. Now, can we say that if there is a 3D, we can expect in scattered pixels. If it is a 2D, we can expect a dense pixels. That is the observation here. Okay. So this observation motivated us to propose one more algorithm, cold distribution. Cold means cloud of line distribution, something is there. Okay. Anyway, maybe next slides probably will get it. What is cold distribution here? This is actually polar domain. See, you are getting theta, and for r, that means in a row you are getting, and theta you are getting here. That means rho theta domain. That's a polar domain here. So what I'm saying, for this algorithm, look at this one. Yeah, this is actually cloud distribution now. This is a distribution now. See, we have taken result of this one, gradient, local gradient difference. That means candidate pixels as input for this one. So what did we observe here? This is number of here pixels are scattered, pixels are not scattered here. So how we can extract this observation? That is a point. So for that we have proposed cloud distribution here. So cloud distribution, what is the input for cloud distribution here? So cloud distribution requires a distance now. So we need to calculate a distance. That means we need some distance here. Of course, simply we cannot give a distance here. So for that, what we did here, so we just labeled each component in the result here. So that means whatever the, of course, even dot is also one component now. We just labeled connected components now. Okay, so that means you are fixing bounding box for each connected component now. So connected component is nothing but what, even dot is also whatever the connected, okay, all connected in individual component can be considered as a connected component. It's all connected now. Okay, if it is, if one character split into two, then it will be two components. If it's a one character without split, without disconnection, it will be, yes, one component now. So like this, so what we did here, so we have labeled in connected components. Every component we are trying to apply cold distribution now. So what is the cold distribution here? Cold distribution requires a distance now. So you are giving a distance as input. Of course, if you give a distance, automatically you can estimate the theta now. Okay, so you are giving distance, so you can estimate the theta now. So it is in rho theta polar domain now. Okay, now the point here is, so for every component, so we need to get distance now. How we can get a distance? And of course, our approach is something, see, our goal is to classify 2D and 3D. So how we can classify 2D and 3D with this observation, with this cold distribution now? That is the point here. So what we did, very interesting approach, interesting step here. Try to understand now. So for every component, what we did actually, we have calculated centroid now. Okay, from the centroid 360 degree, we'll move in a 360 direction to reach the boundary pixel now. See, idea is something like this. See, every character will have a stroke width. Okay, see, as we observed in case of 2D, yes, character shape is preserved. Okay, that means stroke width. What do you mean by stroke width? Actually, thickness of the stroke. That is a stroke width. Okay, if it is a character, then stroke width remains constant for the whole character. So this is a very good observation, very good features to say that this is a text information. Okay, in case of non-text, of course, we cannot expect constant stroke width for the whole character. Okay, so here what happens in the scene in 3D text, we lost information. So lost information in the sense what, we lost even shapes also. When we lose the shape information, definitely we cannot expect in a stroke width, constant stroke width. But in case of 2D, yes, definitely we can expect a stroke width. So this is what I'm trying to extract with the cold information now. How I can extract now? Yes, see, so from the centroid, I'm trying to reach the boundary point now. So from the boundary point, I will come back to get another white pixel now. Okay, another white pixel now. Okay, that means I'm trying to extract a one pair pixel, which one pair of pixels which represent the stroke width. Stroke is the thickness of the character, thickness of the stroke. Okay, that is the stroke width, the distance. So there will be one end and another end now. So there will be 2 pixels now. Okay, I am trying to extract the distance, stroke width, the distance that should be the input for cold, because I want a distance. So cold accept distance as input now. So how I can get a distance? Simply I don't compute in some distances. Okay, first pixel, second pixel, neighbor pixel. Yeah, we can find many ways to calculate a distance between our pixels, but we did not go in that way, because we know very well that in 2D there will be constant stroke weight, but in case of 3D, yes, you cannot expect any constant stroke weight. We know that one. So how we can extract this observation? Yes. So we are trying to get stroke width pair. Okay, pair pixels. So there's a pair of pixels now. So see nothing but what distance now. So you have a two pixels and you know the coordinates now. So this distance should be input for cold now. Okay, so what happens now when you have a constant stroke width? So this is the observation now. Look at the cold now. When you have a constant stroke width, we can expect in a dense cluster towards center. So in center point, look at the center point now. This cluster, this cold is giving in, see, this is a dense cluster now. But look at here now, 3D, because we cannot expect a constant stroke width here. So stroke width varies now because of the loss of information. Loss of information. Okay, so that is the reason. So we don't get a constant distance now. So when you don't get a constant distance, then we cannot expect in a dense cluster by cold. Okay, so this is a difference now. So easily notice now, this is a 2D, this is a 3D now. So definitely, yes, pixels are scattered now. Red pixels are scattered here. Red pixels are, yes, centered. Okay, at one point. Okay, so now this is another observation now. See, it is not so easy. That's what I'm trying to say. Okay, initially we just applied gradient. From the gradient, we got an dominant pixels. From the dominant pixels, again we got a candidate pixels. From the candidate pixels, again we are going for one more step. Okay, now what is that one? A mass feature. See, so previous, you just look at the previous one. As I mentioned here, the pixels are scattered here, the pixels are clustered here. How I can extract this observation? Yes, again we proposed one more step, mass calculation. So mass calculation is nothing but a what? Every ring. So we have defined and I think some radius. Yes, we have calculated an optimal radius through experimentation. And finally, yes, this is actually one circle. There is a one radius, one ring. Every ring we are trying to count the probability of the pixel. Okay, that is what the mass. So mass estimation, it is a different theory. You can go through any mathematics also, any paper. But anyway, what I want here, what we want here, every ring we are trying to extract in a mass feature. So it is actually probability of pixels present in the in each ring. Okay, that means what is happening now? So let us say for every ring we are getting pixels. See, in this case, yes, number of pixels, look at every ring. Yes, we cannot expect anything now, because suddenly there will be some variations, suddenly some random changes here. But here you can see, because of the dense, we can expect an high pixels for few rings, and suddenly, yes, you may lose something. But here that is not the case here. Okay, so now that is what actually mass. So using mass, what you are using, that means in every ring we extract a mass, we calculate a mass. Then I think, I don't know how many features we extract, probably eight rings and eight features. So that will go to the classifier, neural network classifier. We don't use any deep learning here. Just we send eight features as input to classifier. So that automatically classifies 2D and 3D. Okay, that is simple. So of course, what is the contribution and what is the work here? So yes, dominant pixels, we got in dominant pixels using gradient information. From the gradient, again we used local gradient difference something to extract again candidate pixels. After getting the candidate pixels, what we did again? Yes, we observed what is the difference between 2D and 3D. Yes, there will be a dense cluster and there will be some scatter pixels. So to extract this observation, we have proposed cold distribution. So cold distribution, yes, gives clear distinction between 2D and 3D. And finally, yes, mass features. Okay, mass of, so then, yeah, this is just an experimental results. So now look at the data set now. So image level, line level also, we have tested even line level also. So 2D and 3D, and this is a data set information. Okay, we have our own data set is there, and standard data set. Of course, we have collected standard data set from natural scene text database. Okay, these are all actually natural scene text data set. So we have collected whatever the 3D available. Yeah, just we have collected. Now, this is ablation study. I think this is a new word. Probably I don't know whether how many people have heard in this word. So earlier, I think we used to write how we can assess contribution of each step in the proposed methodology, or each step proposed in the method. So in order to show effectiveness or contribution of an each step, in our case, okay, dominant pixels is one step, local gradient difference is another step, code is another step, mass is another step, like this. Okay. Now, ablation study is nothing but what you are trying to show. You are trying to prove that every step is effective. Whatever you proposed, every step contributes to achieve better results. So if you don't include this one, there will be a yes big problem for you. Okay. So sometimes yes, you can expect rejection also. I think ablation, I don't know, maybe it should be medical word. So what we did here, yes, of course, we have done experiments and proposed method proposed without LGD, without local gradient difference. So without result of in a local gradient step result. Straight away we can take dominant pixel as input. You just skip this local gradient candidate pixel result step. Just you straight away take dominant pixels as input for classification. So like this, proposed without code. Don't use code at all. You just draw rings over the candidate pixels. Just send in whatever you get in mass feature, everything you just try to send. That is the way. Okay, proposed with the density. So mass always confused with the density. Okay, density, of course, you're just counting number of pixels. So mass is just an improved version of that one. Not just in counting number of pixels, we are trying to choose, trying to apply some probability with the defined granule. You mentioned in a granule, there will be a ring or there will be a boundary. Within that, again, you are trying to look for something which is important, which has a high probability or something. Okay, that means it is something improved version of the density. So mass and density, so both always get confused. So that is the reason we are trying to show, if we just choose a number of pixels, then what will happen? What is the result now? If we choose mass information, then what will happen? So that means we are trying to prove that, we are trying to show that, so every step is effective and important to achieve better results. That is the way. Okay. And of course, these are all just results. I think no need to spend time here evaluating proposed classification, text classification at image level, text line level. Yes, see, we are trying to test our algorithm, how whether it works at image level, not only image level, even text line level also. Okay, text line level means you are just giving text line as input and see what will be the performance. Okay, so this is our data set image level, standard data set image level, and line data set line level our data set. Of course, line level means we used text detection algorithm to detect the text and then output of text detection algorithm as input for classification. Okay, input for classification. Of course, existing methods are, we have compared with existing methods also. And anyway, see what is happening. Where is our proposed method? Classification image database, okay, existing methods. Okay, now proposed method. Yeah, this is methods of text detection performance. Of course, yeah. Classification. So when you show classification result, of course, one more experiment is required to validate the classification method. So that means if you want to show that a classification is really contribute something, classification is really essential for achieving, for improving text detection performance, then yes, validating the proposed classification. That means these are all actually text detection methods. So every text detection methods, yes, for our data set and standard data set. So we have just calculated text detection accuracy, okay, text detection performance in terms of F measure. So we calculate F measure here. So before classification, after classification, look at now, before classification, just we are sending all images as input now. So without classifying 2D and 3D. So after classification, this is actually after classification. So look at now what is happening now. So accuracy increases now. Okay, look at this average now, average of 2D and 3D. This is 70. 59, 63, 60, and 63. That means, yeah, after classification, accuracy improves. That means what? Yes, classification really contributes here. Classification really makes a difference here. Okay, so this is something, again the same thing, but standard data set now. Again, so look at this average after classification, before classification, 73 and 76, 64, 67. Yeah, like this. After classification, definitely we can expect an improved, okay, high results compared to before classification. So similarly for text recognition also. So of course, since we are getting in lines, so for the lines, again, we used text recognition algorithm. So text recognition algorithm, and finally we calculated recognition rate before classification and after classification. Look at now average now 79 and 91. This is actually recognition rate. Okay, recognition rate, not text. This is actually text reduction rate. This is recognition rate now. Okay, and finally you can observe now after classification. So definitely accuracy improves now. Accuracy has been improved now. Okay, that's I think the whole thing of this approach. Just look at this paper. Probably you can understand. This is a one conference paper. Okay, just recently accepted ICPR conference. Same content I have just presented here. Not any difference here. So ICPR actually there are two submissions. There are two stages. First stage, yeah, submission. Second stage also another submission. This actually submitted in a first stage itself, but we got major revision. They gave chance for us to revise to submit in a second stage. So finally, yes, we revised and got acceptance. Okay. Now another one now. So new common points detection method for classification of 2D and 3D text in video and scene images now. So earlier, so the previous one, we have proposed some method, local gradient difference and code concepts to classify the whole image. Even we have tested the same algorithm on line level also, at line level also. So yes, that was method can work for both line and images now. So this one, yes, so we already presented that. This one is already I think published also. So new common points detection method for classification of 2D and 3D text in video scene images. Okay, now we have just see, I will try to share in what concept and methods proposed here. Yeah, I think introduction is fine. I already explained that one. So even, yeah, person re-identification also, even tracing the person marathon and sports also. Yes, we can use this one. So marathon, sports also. Okay, how we can trace the guy and how we can watch the guy, what how we can understand the behavior of the guy, and a marathon also, what is happening if someone suddenly got in a sick, then how we can trace the guy whether he's healthy, is not healthy. Yeah, those are all the information. So of course introduction is fine now. No need to explain this one. Yeah, this is actually just a motivation for us. See, before classification, this is actually image with a 2D and 3D text. Okay, so now this is a 2D text and this is a 3D text now. Now recognition result, you look at the recognition result now. So recognition result of, yeah, these two are recognition methods, existing methods, codes are available. You can check it now. Methods before classification. So before classification, see the what is happening now. Adventure, something different. Adventure, shark box. Yeah, it's you can see results are not correct now. Recognition result are wrong here. That means in wrong recognition before classification. So that means when you applying recognition algorithm on 3D and 2D, then recognition methods report poor result here. Okay, the performance degrades. So how we can improve? Okay, that is the point here. So after classification, see adventures is very clear now, is correct now. Shark is correct now, and yes, adventure and shark, this is another method now. So that means before classification it is all incorrect result. Now say you are missing now, this is the recognition result is not correct now, so here recognition result is correct. So that means here the only the change is approach, motivation, everything is same as the previous one. The only change is here we take text lines as input for classification. Earlier case, we have taken full image, 2D image as input. Okay, so here 2D text and 3D text as input now. So how we can solve the problem? So what is the idea here? So idea probably just straight away go to work text lines detected by existing methods. Okay, it's noted by we have proposed method intuition stroke width. Yeah, it's again I'm going back to the stroke width information only. Okay, so even in a previous method also I have mentioned. So before giving to the cold, before applying the cold distribution, we are trying to extract the stroke width distance as a input for code information. Again, I'm going here also same concept here. Okay, see 2D and 3D, because of the shadow, what happens you can expect in some common points here. That is what then idea here. So what do you mean by common points here? The common points is something like this. Because of the shadow, we can expect one more stroke width here. This is extended stroke width here. So stroke width means what is the thickness of the character, okay, thickness of the stroke. That is what then stroke width, the distance we define. Okay, now because of the shadow, it is also another stroke now. So since shadow is there, you can expect in one more stroke width here, one more stroke width here. There will be a common point something now. My target is these common points. So that means what? If it is a 3D, there will be a shadow. If there is a shadow, then we can expect some common points now. Those common points are nothing but a what? So this side you can expect in a stroke width the distance of a shadow. This side you can expect a text, actual character. Okay. So in case of 2D, since there is no shadow, definitely you cannot expect any common points here. So in 3D, you can expect a common points here. That is what then observation, that is what the idea here. So you can propose your own algorithm here. So what is important here? Idea is important here. See, in the previous algorithm, we are trying to extract any extra information which is present in the images now. Extra information. So that means in a shadow is a extra information. Earlier we have just defined shadow is something extra information or unwanted information. So we are trying to eliminate that information. But here, because of the shadow, we are expecting in a common points now. See, slightly some different observation, different idea, and different approaches now. Okay. Now, that's the whole idea. You look at now. See, what is the clue now? See, we have calculated a stroke width for every pixel or every character. Okay. Just we stroke width algorithm is there. Just we use a stroke width algorithm to calculate a stroke width of every pixel. So we have just plotted histogram here. Okay. So distance, histogram means what? Distance, we got in a distance, you just in a plot histogram here. So y-axis will have in a frequency now. So for this is actually 2D, this is actually 3D now. See, for 2D, what happens? You're getting some kind of a regular shape, some distribution here. So like maybe normal distribution, skewed normal distribution here. But here, you did not see, this is something totally arbitrary distribution. It is not, you cannot say it is a normal distribution. It cannot say it is something in a regular distribution here. So for 3D, why? That is a point here. That is a point here. See, I have already mentioned here, in case of 2D, stroke width distance will be constant. So what is happening now? So every character, that is what our assumption also, every character will have in the same constant stroke width distance. So definitely we can say because of the more characters, because of the characters, because of the text information, you are getting somewhere else in some constant stroke width, which represent in a stroke width will have high values, will have a high number now. So that is what we can expect high peak here. Maybe this is the stroke width 0.2 to 0.3. Of course, these are all normalized values, not actual distance. It's, of course, always we can expect 2 pixel distance as a stroke width. Not 1 pixel, 2 pixels, 3 pixels maximum. Of course, it's a big font, it will be big stroke width. But in our case, yeah, some distance is giving an highest value, and of course, we cannot expect an highest value for all the stroke width distances. Because if there is a stroke width, if a stroke width distance represents the character, then you will have a constant value. So that value will be higher. That will be peak. That will be the peak now. But here, see, in case of 3D, yes, as I mentioned earlier, we cannot define a stroke width here. Even if we extract the stroke width distance, that may not be the constant value as 2D image. See, that is the clue here. That is observation here. So this is enough to say that your algorithm works well. Okay, so for this what we did here, so dominant point detection. So earlier I used just in a gradient or something. Now we are trying to propose one more algorithm here, dominant point detection using generalized gradient vector flow. So gradient vector flow is one concept. Okay, it is already there in the literature now. So you can just check what is the concept. Now you just modified that concept, because we know that what are the drawbacks of conventional gradient vector flow concept. So we have modified that one. So modified so that it gives better results for dominant point detection. Okay, so we have proposed something in modified gradient vector flow. So to find dominant points here. So what is the approach here? What we do with the dominant points here? What do you mean by dominant points here? See, as I mentioned, see what is the special characteristics and the special property of the GGVF gradient vector flow. If there is an edge here, what happens? You can expect two arrows opposite each other. That means there is a one pixel here, one arrow pointing towards this pixel, another arrow pointing toward this pixel. That means opposite arrow symmetry for every edge pixel. This is what the property of an GGVF. So of course, conventional GVF, it was not good at corners. When there are some corners, when there is a corner, that conventional GVF was not giving proper arrows now. So that is the reason we have improved. So we have modified conventional GVF as modified. That means in a generalized GGVF, it works very well. Even if it is a corner, even if it is a cursive nature, even if you lose in a low contrast, yeah, definitely it gives a correct arrow now. So what is the property here? This is a well-known property now. If there is a edge pixels, we can expect opposite arrow symmetry. Okay, that is what that means. If pixel satisfying this opposite arrow symmetry, then we can say it is a dominant pixel. Okay, you just extract those pixels or retain those pixels and remove other pixels which does not satisfy opposite arrow symmetry. Okay, yeah. Candidate point detection using a distance neighborhood symmetry. Yeah, just will go finally common points. See, that is approach here. See, for 3D, definitely we can expect a more number of common points because shadow is present. In 2D, since there is no shadow, how we can get common points concept? There is no common point at all. Okay, of course, due to some background information, we can get any common points, but that's okay. But when you compare to 3D, definitely 2D will have a very less number of common points, but 3D will have an exact number of common points. Okay, that is the whole approach and whole idea here. Okay, this is what you see down the GGVF and how it gives in a GGVF for 2D and 3D. See, this is what in a point. This is a edge pixel. This P1 and P2. Look at the arrow now. Okay, this is the arrow now. Arrow is pointing towards edges. Okay, arrow is pointing towards edges now. So P1, this is another point, and P2. Anyway, what I can say, opposite direction symmetry. So opposite arrow now. So see arrows now. How you are getting an opposite arrow. If there is an opposite arrow, that means a pixel satisfying opposite arrow, dominant point. This is opposite arrow. Okay, so yeah, this like this in a see opposite arrow. Okay, that is a property of a GVF information. This is actually the result of dominant points. You look at now, dominant points are nothing but I want to look at now all edges are represented by dominant points. That means the dominant points indicate dominant points includes all edge information here. Okay, even doesn't matter that is a 2D or 3D. That is what an advantage of GVF information. That means this algorithm works well for both 2D and 3D, because of course you're just checking every edge pixel, and yeah, and there is a condition whether this pixel satisfies this opposite arrow or not. If it satisfies, yes, we just take it. Okay, we just classify it as a dominant pixels. Now this is the result of dominant pixels. Now next, candidate points detection. So dominant points, these are dominant points now. So candidate points, how to detect the candidate points? So for this, again, I'm trying to explore again stroke width distance information here. So what we did here, so every point we are going for the 8 neighbors. There will be 8 neighbors. Again, we calculate the distance between point with all 8 neighbors. Dominant points. Okay, dominant points. That means we know very well that if there is a text, if there is a stroke width, then there will be a constant stroke width information. Okay, some kind of symmetry you can expect now. So what we did here, okay, for every dominant point, we just go for 8 neighbors and calculate a distance between 8 neighbors. Okay, then plot a histogram here. So plot a histogram for those distances and choose the distance which gives the highest peak, which contributes to highest peak. Okay, those pixels are considered as a candidate pixels. That means there are some values, and of course every value will have a corresponding pixel. Okay, corresponding pixel. So this value is contributing to highest peak in the histogram. So highest peak in the histogram, those pixels, the values corresponding to that pixels, okay, pixels corresponding to those values are considered as a candidate points now. See, this is the result of any candidate points. Definitely, we lost compared to dominant points. Compared to dominant points, definitely number of candidate points should be less. Okay, compared to dominant points, and of course, our intention is that one only. We are trying to reduce background information and unwanted information here. So we are trying to extract and trying to detect the important information which really gives some distinct features. So common points. What is the common points? Yes, the concept is again I'm going back to the stroke width only. So here, so C1 and C2, this is actually the neighbor C1, C2, C3. These are all neighbor pixels now. So we are calculating the distance between this and this is a one pair now because we've already calculated. So every pixel will have an 8 neighbors. We are calculating in a stroke width or a distance between 8 neighbors now. So these are the 3 neighbor. For this is the neighbor and this is the neighbor now. Okay. Anyway, now what we do now for, so this is a one pixel now, C1, C2. Now what we do now? What is the distance now? What is the second pixel now? Okay. What is an adjacent pixel? What is the distance now? If distance are same now, that is what we define a neighborhood symmetry. So that means this pixel, what is the distance now? It is the same. So what is the distance now? It is the same now. If these two pixels satisfy and these two pixels will have a same stroke width, then we can say it is a neighborhood symmetry. Of course, we check actually the one point and both and adjacent and neighbor and left and right or in top and above, above and below. So top and bottom. So this is a point and this is a point, this point. So we check, okay, distance point from this to this and this to this. Okay. So if all three same, then we can say it is a neighborhood symmetry. That means we just choose those points. So actually, these are all actually common points now. Common points now. So common points actually visit what happens 2 times now. Because stroke width for this one is the same. This is a common point now. Stroke width is here, stroke width is here now, left and right. So that means this common points hit by 2 times now. So common point hit by 2 times. Okay. So those common points, so neighborhood symmetry candidate points, two adjacent pixels marked. Okay, this is a common point detection for 2D. Yeah, so 2D and 3D, yes, though the pixel hit by twice, because it's a common point in the sense what, of course, if how can I define it as a common point? Because this is a stroke width, another stroke width. That means for this stroke width, yes, again you are tracing this point, you are visiting this point. For this stroke width also you are visiting the same point. So that means you are trying. So the point which hit by 2 times is considered as a common points now. Okay, now I think that's all our idea now. So now just we are trying to extract some features using common points now. Let us say these are the common points. We just in a group, this is a number of pixels between C1 to DR1 and DR L1 and L2. So this is a one group for us, this is another group for us. So for each group, so we are just calculating a mean and standard deviation. Yeah, like this, and we just extract some features for classification, because yes, we know very well that common points, so whatever you extract from the common points, that will be the distinct information, that will be the distinct information for classification. We know that one. So that's what, so whatever the things associated with the common points, definitely good features. Okay, definitely good features. So just we extract in features using group 1 and group 2. So yeah, mean and standard deviation. So like this, even for candidate points also, not only common points. So for candidate points also we extract, because candidate points also give some information. So we extract the mean and standard deviation. So of course, before that we are trying to group in a group 1 and a group 2. We are to try to make in two groups, left side on group, right side on group, because the common point. So then for each group we are calculating some mean and standard deviation. So that will be the feature extraction, and finally that feature will go to classifier. Okay, that's all. See, idea almost same, but different approaches. In a previous algorithm, we just introduced a local gradient difference. And next classification, we are trying to exploit the same idea, same observation, but in different way. Okay, something we have defined in the common points concept. Earlier, we did not define a common point concept. Okay, that is where, problem is actually, according to me, problem is same. Classification problem, there's a classification problem. So just what is the difference here? So input, you are giving full image as input, line as input here. When you give a line as input, then you will have specific information now. So not necessarily you should think so many things here. Not necessarily you should think in complex algorithm, because text is in almost, we have removed background information now. The complexity has been removed now. Just only text available now. So when you have a text information, then it is easy to solve the problem. Okay. So now this is a data set. Sample images of a 2D and 3D text from our dataset and standard dataset. Of course, so we have in our own dataset, and the standard dataset means actually these are all actually natural syntax detection datasets. Okay, not our dataset. So of course, whatever the things available, these are all not 3D but 2D text dataset. But of course, sometimes you can see few 3D lines also in the dataset. So we have selected those things manually. We collected. Okay. Okay, then just results. Yeah, again ablation study. Experiments using in a canny edge pixels, experiments using only dominant points, experiments using only candidate points, experiments on proposed common points. Okay, see, if you want to prove that common points is better than canny edge, of course canny, whatever the canny gives its edge image, now we can consider that one as a dominant point. Why you are going for the separate step for dominant point detection? Again you are proposing one more step for candidate point detection, then common point you are defining now. So why don't you say that all edge pixels are common point? Why don't you say all edge pixels are in dominant points? That is a question here. So yes, this is very important step for you to prove that yes, every step and whatever you proposed in the methodology should be effective, should contribute something. Otherwise, how? Simply you are proposing some method, simply you are proposing a lot of steps. What is the use of that? How we can understand, how we can prove that every step is important, every step is effective, every step is contributing? How we can prove? Yes, this is what an evaluation study. Okay, all edge pixels. Okay, now this is what in a 69 point. It's definitely yes, there is a accuracy now. Only dominant points, yes, increasing now. Candidate points, yes, decreasing. See, dominant points better than candidate points. That means we lost information here. Dominant points, of course, it has all information now, including unwanted, even everything. So somehow okay. But here, what is happening? All edge pixels, of course, you are getting a lot of information, but it's very difficult for you to extract good information from the bad information, because here unwanted is more now. So in all edge pixels, unwanted is more. That is the reason we are losing accuracy. Here, yes, unwanted is less, but wanted is good. So something we are getting better result. But here, yes, we lost some vital pixels now. So candidate pixels we lost. Of course, common points is always better, because exactly we're going with the point. Okay, common points, yes, automatically it will classify 3D and 2D. Okay, this is using proposal method on different data set. Okay, now yeah, we have got some images from this data set, this data set, this data set. We have just calculated the classification and experiments using proposed and exit methods on different data set. Okay, our data set and the standard full data set. Yes, look at now. mm, yeah, average 43 and the proposed method 92, and the proposed method standard full data set is actually low, our data set is high. So yeah, then recognition, of course this is a text line, there is no text reduction experiment here, because in previous work we have shown text reduction experiment. Now text recognition experiment, because the line as input, when you line as an input, yes, we should go with the recognition result here. That means we are trying to show that before classification what happens, after classification what happens now. So before classification it's already, yeah, same thing only, no, there is no difference compared to previous step or previous method, previous talk. Yeah, 2D and 3D we just combined here, so we don't classify it as a 2D and 3D. So this is again a recognition methods now. So we are, yeah, this is what an results recognition rate we got when you combine 2D and 3D before classification. So after classification, the C2 for 2D is increasing very high, so 94 is very very high, and 3D also is increasing. And average, look at 91, where is 91 and where is 78? So 90 and 85, this is a very big difference now, significant difference now. So similarly for another data set, 2D and 3D is combined. This is actually after classification. This is the one. So that means, so what we can understand, that what we can justify now, yes, if we don't classify, then accuracy is low. So we cannot expect any high performance of the recognition method. So when you classify, definitely we can improve performance of recognition performance. Okay, so that's the thing. And yeah, I think conclusion, just go back to, just I will show this paper. This is already published now, so recently 2020. Actually he's actually master student working with me now. And yeah, he's actually he's Gujarat, what is it? Yeah, Dhirubhai, yeah, Ambani is working over there. Yeah, this is actually collaboration work. You look at the paper, the same thing I presented. Yeah, this is a one piece of paper. If you want to have one conference paper, yes, like this, and you should contribute something. See, problem is same, but just I defined this problem in a different way, and of course I solved in different way. Yeah, that's a way of thinking. Okay, I think, yeah, I think that's all. Okay, maybe can close this one. Next topic is 3D video text reduction system. So yeah, as I mentioned earlier, so initially we started classification. That means, that is also one way of classifying the problem, because our ultimate goal is to improve text reduction and recognition performance for 3D video. That is what our ultimate goal. So first let us classify so that we can improve text reduction and recognition performance. That is one way. Now we are trying to develop single method. That means one method that should work for both 2D and 3D text reduction. Okay, the text reduction video. So this is where the complexity increases now. Okay, so of course here there is no classification. So straight away we are trying to develop like a unified method or single method for detecting both text text in both 2D and 3D videos. Okay. Okay. Now this is actually what I'm saying. This actually just under revision now. So I don't know what will happen. So they will get an acceptance or rejectance. It's all depends on the reviewer. So we have submitted, and finally, yeah, it's very good work. Let us see what happens. Anyway, I'm trying to share this information, though it is not published. So don't disclose. Just try to understand what I proposed and how we proposed and why did we propose like this. And just you try to get an information. So no need to disclose to any other person. Okay, here what is our this is actually motivation. Look at this one. See, this is 2D, all 3D, right? Okay, all 3D. Now look at now. This is actually craft, DBNet, PSCNet, and proposal method. These are all actually existing methods. So this is a motivation. That means you just yes, if you want to confirm this is a problem is something now, problem is complex, problem is not been solved, then how we can confirm that one? How we can show? Yeah, this is one way. So just if you write so many papers and refer so many papers, just sometimes and people don't believe. So people won't accept those things. So in that case, what you have to do, you try to show, okay, existing methods. These are all actually latest existing methods. These are all deep learning based methods now. So we just tested those methods on 3D images here. So of course, yes, methods are giving results, not really bad, but definitely, yeah, methods missing the result. So we don't the methods do not give an exact bounding box, fix an exact bounding box, or sometimes they miss in one character, two characters, or maybe end characters, and fixing bounding box is not correct. So like this, there are some issues with the existing methods. That is obvious because methods have been proposed and developed for 2D, not for 3D. So how you can expect? That is a main drawback of deep learning. So because the method is not learned and trained with the new samples that contains 3D, 3D or 2D, 3D and 2D, then yes, that's a problem. So now look at that is a problem. So proposed a method, yes, we proposed a method which works very well for 2D also, 3D also, and of course, yeah, fixing bounding box also no problem, arbitrary shape also, background complexity also doesn't matter. So we are getting a good result. That means what we are saying here. That is this actually motivation. That means we are trying to say that. So whatever the methods are developed so far in the literature survey may not work very well for 3D video images. That is what in our intention here. Okay. Now this is the motivation. Now how we can solve? Okay, this is a related work. Of course, when you go to deep learning methods, yeah, it depends on different application and different problem also. In my area, so we can divide into three categories or in four categories. So of course, regression and anchor based, maybe we can combine both also, it is fine. So no need to define separately. But some people, actually reviewer ask us to separate like this, so we have done like this. But actually regression based and anchor based methods can be combined as a one, because regression based also following the same thing. So it is something like, I don't know, I'm not in a deep learning guy really how it works in regression based and other things, but generally the concept is like this. So it just consider the whole box as a one object, then try to fit. Okay, regression means you are trying to fit or trying to approximate, trying to get relevant information. So now anyway, what is the input for this whole text box? Because it's a ground truth, you'll have a ground truth. You know how to trying the things. So you have a ground truth in the sense what you know the bounding box, you know the text line, everything you have information in hand. So now they are trying to learn in this way. They take in whole box as the input, then they try to see what is the regression line here, what is the bounding box here, what is the connection here, what is the relationship here, like this. So that is what in one kind of category. So but as I mentioned, this will not work for 3D, because when image contains a shadow, how you can fix it? Because you are taking the whole text as a one box and as input, but that is okay for training. When shadow is there, so shadow, when there is a shadow, then bounding box will be something different. So definitely, whatever you trained with the exact bounding box, so it will not work for the 3D. Okay, so that is a problem with the regression based method. So anchor based method here, what is happening? Yes, it's also same as a regression based, but only thing is they'll try to define this is an anchor. So anchor in the sense, what is a reference character? So from the reference, they'll try to, yes, get in the next like this. So reference, from the reference, they're trying to propagate or get an extra information, try to get a neighbor information. So that means this, the problem is actually anchor only. How we can decide this is the anchor, this is the reference, this is the base. So when something goes wrong here, then whole thing will be wrong, whole thing will be whole thing will be something incorrect results. That means that results in wrong answer. Okay, so that is part of the problem. But of course, so segmentation based method, that is actually powerful and robust, and there will be a lot of scope for introducing many things here. So because segmentation based means they are trying to segment the character, that means they will try to look for, if it is a one text information, they'll try to split into so many things. So they'll try to divide. So they'll try to extract the local information, not like a global information. So anchor based regression means they'll go for global, take in a whole as a one, and finally they do something. But here not like this. So they'll try to extract information of every character also, even every pixel also. So that means it's something like a bottom up approach. So you are trying to get pixel, from the pixel next bottom up, you are trying to grow your method like this. So definitely it will be robust, because you are working at a pixel level, you know which pixel is dominant, which pixel is invariant to distortions, which pixel is invariant to this one, or everything. So since you are working at a pixel level, you can do anything now. Okay, in that way segmentation based methods really better than previous category. But yes, again for 3D video it is a problem now, because shadow character, shadow is shadow actually, yeah, you see, there is a one I just try to give you an example. So if you are a text if you know the text reduction, and if you have some knowledge of a text reduction, then it will be easy. So generally what we assume for text reduction, characters, if we take a character, the pixels of the characters will have any uniform value. That is what our assumption, not for the whole line or whole word. At least when you take in a character, because we write also, even handwriting also, it is the same writing will be there, one character. So at least for that character, when you check in pixels of that character, so values will have an almost the same. So we say it is a uniform value. Shadow also will have a uniform value. This is the problem here. So that means uniform value is also uniform value. When the method developed based on this feature or this an observation uniform value as a hypothesis, then it is difficult now. So even shadow is also considered as a something correct according to the method. Okay, according to the observation. So that is a problem. That means when there is a shadow, this will always will have a conflict with text pixels. Okay, so that is a problem with a shadow 3D video. So hybrid methods. So yeah, this is what actually I do, because I am not a machine learning guy. So I cannot contribute anything to machine learning or deep learning. So generally what we do, so we try to propose one section feature extraction to solve the problem. Then output of feature extraction, or maybe some, yeah, we can say even some people say handcrafted features also. So a result of feature extraction should be input for deep learning. That is the way I'm just going all the time in combinations. So if you, because yeah, that is the way yeah, this is my approach, this is my thinking. So why? Because I believe just deep learning is not good, just a feature extraction is also not good. So let us take an advantage of a deep learning also, let us take advantage of a feature extraction also. Handcrafted features, if you use handcrafted features, definitely you no need to train your classifier or model architecture with so many samples, not necessary. Because feature extraction gives removes a lot of information and gives exactly the relevant information now. So that means you are taking relevant information as input for deep learning. So obviously your learning or any classifier should give a result here, not necessarily even deep learning. So that means indirectly what I'm saying, I am trying to use deep learning as a classifier, not as a feature extraction, not as a solving the whole problem. Okay, so that is what in our thinking. So in that way we should contribute well. And of course, so I always believe that if we go in this combination, so we can justify there is a robustness, and the method is robust, method is independent, method does not depend on large number of samples, and the tuning parameter is not necessary. Yeah, and generalization also, like this. So there are many advantages if you combine both the feature extraction and deep learning. If you just use deep learning, yes, there will be some drawbacks. If you use just feature extraction, again there will be some drawbacks. So okay, you're trying to take advantage of both to develop a method. That is what we did here. So yeah, many people think in this way. This is a whole proposed approach. Again, yeah, look at this GGVF. I've already introduced this GGVF, generalized gradient vector flow. Yes, again we are using the same same concept here to detect dominant points. Same step. So we are getting the same step, no change in the steps. So GGVF, so dominant point detection, exactly the same, only we are just checking the opposite arrow symmetry, the same property. So using GGVF, so GGVF always gives an arrow. That is what an output of an GGVF, gradient vector flow. So when there is a edge pixels, we can expect an opposite arrow symmetry or direction symmetry. That is a property we define, okay, for dominant points. Okay, that step is already finished. Now candidate points detection. Yes, for this we proposed something new concept. So the what is that new concept? Where is that concept? Input mask, deep learning. Can, yeah, this wavefront concept. Yeah, this is what in a new approach, new contribution here. So we proposed we taken a dominant points as input, input to wavefront concept. This is a new concept we introduced. Of course, this is not in my concept. It's already used in what not medical, something path. I remember path identification, shortest path identification, or something, shortest path calculation estimation, something. Yeah. Anyway, we understood this concept and we observed the properties of this concept. Then finally we modified, we adopted, or we modified this concept for our problem. See, earlier I used something local gradient difference and cold distribution also to get any candidate points. Now yes, I just change the steps. Now concept is same, idea is same, solving approach is same, only the change is approach, only the change is concepts. Now that means I am trying to bring in a new methodology or new concept here. That is where we can contribute to the work. Okay, now candidate points as dominant points as input for this one. So how we can detect the candidate points using wavefront concept? What is a wavefront concept? So wavefront concept is nothing but a what, I think you know waves very well. So once how wave forms, okay, so it uses a previous wave energy for next wave. That is what in a wave, you can see waves, how it goes in waves. Same concept we brought here. So of course here the 8 neighbors pixels will be there. There is one pixel and 8 neighbors will be there. We are trying to use 8 neighbors to predict something. Okay, so that should be the candidate points for us. That is true everywhere. It's the same only. We are trying to use, and for every approach we are trying to use a neighbor information to get something. It is the same for every step, every method, every paper. But the only thing, only the change is here, the way we get the candidate points, the way we decide the candidate points, that is what in a different here. So of course wavefront concept requires what? Not only angle, not only direction, speed also, because speed is very important. That's one parameter here. So that means we are trying to include speed as a one parameter, one property to get the required information. So gradient information, it just gives in direction. But along with the direction, if we had speed also, then yes, it makes some sense. That is what in the justification. That is what in a good property here, because we believe that if there is a edge pixel here and 8 neighbors, if 8 neighbors should have some common property, should share some common property. So if pixels share common property, then you should get something. That means whatever you predict, it will be yeah, this property will be reflected. If it is a non-text, that means let us say it's a one text pixel is there, surroundings are not non-text pixels because it's a non-text pixel, not text pixel. If there is a text pixels, definitely we can expect in neighbor pixels also text. Okay, 8 neighbors will have a text pixels. But if it is a non-text pixels, then I don't think you can expect in something different pixels information, different pixels. When you have a different pixels, we cannot predict something expected. Okay, that means something we can a regular pattern, let us say regular pattern. Since 8 neighbors are same, almost same compared to the candidate point, then definitely we'll have something regular pattern. Okay, that is what is the concept of your friend concept. Maybe you can see that some sample results and intermediate results of the steps. Okay, then we used input mask. Actually we proposed here some deep learning technique here, deep learning model, to get in this probability map. This is actually yeah, my student is very good in deep learning, so he brought some concept, and finally we got in a probability map. From the probability map, this is another contribution here, adaptive B-spline curve fitting. Because we have seen in one paper in the CVPR, computer vision and pattern recognition, they proposed Bezier curve fitting. Okay, adaptive Bezier curve fitting. So when we read that paper, adaptive Bezier curve fitting, then immediately we started, we know, I think everyone knows, I think most of the audience know very well, B-spline is better than, is a computer graphics topic. So B-spline is better than Bezier curve. So we knew that, okay, B-spline is always better than a Bezier curve. So just we have, just we replaced Bezier curve by B-spline curve. And finally, of course, it should give a better result only. So Bezier curve, yeah, there are some drawbacks. So B-spline always go with the control points. Of course, here also they will have a control points, but local will decide this control point based on the local information, not with the global information. But Bezier curve requires a global information, but B-spline requires a local information to decide the control point. That is where I think always local is always robust information. So local always gives an extra information and more information. If you want to remove, you can remove it. But global, yes, when you lose in local information. When you lose information, restoring is not so easy. When you lost information, yes, getting back, no, it's difficult. Yes, we have information. Not only we have information, we have extra information. Yes, removing extra information is easy. Removing unwanted is easy, but restoring lost information is difficult now. So of course, everyone follow the same thing. So that's the idea. That's a research mind. Okay. Now here in this work, GGVF, that's also contribution here, and candidate points using wavefront, that's a new concept we introduced here. So that is another contribution, and adaptive B-spline curve fitting. These three are new contribution. That is the reason, yes, we got major revision from this IEEE transactions paper. So this is what, some kind of, yeah, you can imagine, okay, this should be the contribution for one IEEE transaction paper. Okay. Now, of course, a video means, when you say video, this is one more thing I need to discuss with you. See, as I mentioned in the beginning itself, video means you will have in a time information, time parameter, temporal information. So if we mention a video, people definitely expect what kind of video information you used, and what is the effect of video information, how you are exploring video information here. So how you are connecting video information with your results. Otherwise, you just say images, then it is fine. If you mention a video, then you have to bring concept of, at least you have to explore the temporal information. If you don't use the temporal information, then it is not video at all. This is the problem here. So now, since our target is text reduction in a video, what we did here, we have just chosen a 3 successive frames. Of course, per second, you will have a 25 to 30 frame. Of course, it depends on the device. So let us say 25 to that is actually very standard and a common one. So we will have a 25 duplicate frames per second. Okay. So now, of course, I don't want to use in all 25 frames. Okay. So because all 25 frames are duplicate, we know very well, because per second you are capturing like this. Okay. So now, so just we have taken a 3 successive frames, and of course we perform simple average operation. So that means we are getting an average image. Average is nothing but a filter concept. It enhances, because it's averaging, it enhances some information. Of course, not only enhancing, it introduces some noise also, some artifacts also, because average, that is what the average filter. Probably, yes, you know, image processing, then you will, yeah, you can understand easily. Average is the thing, but what, yeah, it's a filter, right? It's a filter. So it not only enhances, but also introduces noise information. Okay. So because average is actually floating point number, you are trying to replace the floating point number, real number. So when you are replacing integer with real number, definitely you can expect some kind of an loss, some kind of an approximation. So it's not so easy to get any exact information. There will be some kind of a noise and some kind of an artifacts. Okay. Anyway, that is the image processing concept and image processing class. So that's not necessary here, which is not necessary, not required here. So now, yeah, just we have taken average frame as a average frame. Just we perform a simple operation. Then it's just an average. Then this average frame as input for us now. That is input now for video text reduction. Yeah, this is what in a generalized, and we have shown on sample here. So this is a conventional GVF. Look at now what we expect for. I think as I mentioned earlier, if there is a edge pixel, we should expect an opposite arrow. That is what and we want. That is what the property of GVF. So this GVF, of course, it gives an exact, especially in these cases, you are getting an exact, you can expect an opposite arrow. Yeah, that means a straight edge is no problem. When there is a curvature, then yes, we don't expect an arrow, opposite arrow. That means that is a limitation of this conventional GVF. Okay. Now this is opposite arrow, but this is not. This is okay for this straight line, but for curve line, yes, we are not getting this one. Exactly. Now this is the same thing for GGVF. This is a modified and improved version of an GGVF. Now we are getting an opposite arrow for this even curvature also, for this also. So that is where GGVF is always gives an improve, improve result. That means you can, yeah, you can get any improvements. You can expect any improvements. Yeah, because we are getting an, we don't lose information here. If you use a GVF, conventional GVF, we are losing pixels here because these pixels do not satisfy the opposite arrow symmetry. So we lose these pixels. But here, yes, we get this pixel. That means there is no loss of information here. That is advantage. Again, same thing now. So both 2D and 3D, this is a 2D and 3D now. See, look at this opposite arrow. This is a pixel and we are expecting opposite arrow. Okay, for this opposite arrow. So, okay, yes, same thing, only same condition. So if the pixel satisfy this opposite arrow symmetry, direction symmetry, then we can say it is a dominant points. It's the same thing. Okay, see, look at the dominant points now. So we got this actually gradient image, and then this a dominant point. Okay, look at now. So we have removed this gradient dominant points itself a very good approach, very good step to remove background information now. So just you can see only foreground and text with something, some non-text information, but we have removed almost background information. Okay, look at input images. Okay, there's no input images. Yeah, now wavefront concept. Okay, what is a wavefront concept? Actually, I already explained now. So that means this is in a center point now. This is actually vertical. Huh? Yeah, this is vertical and horizontal. Yeah, these are 2 points or wavefront points, and this is a center point. And finally, this is a predicted point. That means these are the boundary points now. See, this is something like this. You know the starting point, you know the boundary point now. What is this approach? What is this wavefront concept? So you know the starting point, you know the boundary point. So now you are trying to estimate how many ways to reach this boundary point. And you are, after finding in many ways, after exploring in many ways from here to here, so reaching this from this point to this point, then finally you choose the minimum cost. That means the path which gives which gives a minimum cost. Okay, so that means you're trying to see the best one in the sense what minimum cost. Okay, it should not be expensive. Which one is which path gives a, which path is less expensive, gives a less expense since we consider. So that means, see, this is a very simple concept. So there is a starting point, there is a boundary point now. So from the starting point to boundary points, so we just, I think there is a R value, we are just changing the T value. Yeah, we are changing the T value, T equal to, it's actually range between 0 and 1. We are trying to change the values. So when you change the T values, automatically you're getting some direction. We call actually tentative values. So that means for one starting and one end point, you are getting so many tentative values now. Out of that, so based on the cost function. So we have defined some cost and weightage. So according to the formula in yeah, wavefront is actually a well-known concept. If you open a physics, automatically you can see the formula and everything is there. So weightage and cost, then we'll choose the best one. So that means what? Every boundary point you are getting one tentative value. So that means we are getting in a six, because six boundary points here for vertical, this vertical. So six tentative values we are getting now. Again, six more tentative values for horizontal. So 12 values we are getting for one point, one window operation. Okay. So that means now we are trying to understand what is the distribution of 12 values. Okay, here horizontal, maybe we can extend even diagonal also, diagonal wavefront also, that's also possible. So just we are just in this work, it is limited to only horizontal and vertical wavefront. Probably yes, we can extend that one also. Maybe next work we'll try to extend for diagonal also. So this diagonal also, maybe we'll get in some extra information here. Okay, so that may be possibly probably the extension of this work. So now what I'm saying here, so there's a boundary point, there's a starting point here. So every boundary point, so we are varying some t values. Anyway, it is something like an interpolation formula. There is interpolation. So there is interpolation. So through interpolation, you are estimating some boundary points here. So some path here. What is how many paths from here to here? So finally, we choose according to the cost function. We choose the best one, which gives a minimum cost. Okay, in this way, we are trying to choose tentative values. Okay, 12 tentative values for each point. Okay, but of course, what is the idea here? I think as I mentioned in the previous GGVF, yes, we are trying to explore only the gradient direction, gradient information and gradient direction, magnitude and direction information. But that one does not include the speed. But here we are trying to include the speed of the motion. Okay, speed of the, not only just direction, speed of the motion. That is what the advantage of an wavefront here. Of course, see, when pixels, neighbor pixels, as I mentioned earlier, so pixels share some common property. Of course, speed should be same. So this is a one candidate pixel. Surrounding pixel should have a something relationship on speed also. So how we are saying that uniform values, uniform magnitude, uniform direction, similarly uniform speed, constant speed, something. That means even speed also one kind of a property here. That is what we are getting from the wavefront concept. Okay, yeah, that's all the approach, that's all the idea here. So these two are, look at this one. So we get in 12 tentative values now. So just if we just in a plot a histogram and some graph here, so 12 tentative values, some values are there. So just frequency, look at some kind of a pattern for the text. This is sometimes we get a nothing. So it's arbitrary. We cannot expect anything now. At least we can expect some peaks like this, but here, no. That is what anyway I observed. So that way it is true also. If it is a text pixel, if it is a really true text pixel, definitely the neighbor pixel will have a something common property. Okay. So when you have a common property, definitely that should reflect in the graph. So wavefront, we are getting in a 12 tentative values. So when you plot a histogram or when you plot a distribution, definitely, yes, there should be some reflection in the graph. But non-text, what happens? Non-text, what happens? Because you don't expect any 8 neighbors, same 8 neighbors. You are getting in a random values here. Because now it's a non-text, it's not in a text. So because of the random values here, you are getting the random tentative values here. So definitely distribution, you cannot expect any regularity, regular pattern in the distribution. Okay, so that is what the final result. Look at the candidate points for the both and this one. See, so now this is the candidates compared to previous one. Yes, we can see, yes, some of the pixels are removed here. Okay, so now, yes, now this is adaptive B-spline polygon curve fitting. See here, we did something here. What we did here, of course, from the candidate pixels, from the candidate pixels, these are the candidate pixels. If just we perform some morphological operation, of course, before performing a morphological operation, what we did here, we just go back to canny edge images of input image to extract components, edge components from the canny. That means every candidate pixels, okay, for every candidate pixels, we are trying to go back to the canny to extract the components from the canny. That means corresponding to candidate pixels, we are trying to extract the edge components from the canny edge image of the input image. Okay, so that means we are getting edge components here. Okay, So then we try to morphological apply and morphological operations to combined as a component now. So this one, because what, because see, for next step when we are, because we are trying to propose adaptive B spline, that one requires some reason. So not individual small components and small pixels. So we know that. So since when there is a text information, yes, we know that our approach definitely, this the candidate points detection, definitely it uses a cluster pixel. We know that one. So when you have a cluster pixels, yes, we can combine all the pixels as a one component. So that's what we did here. Of course, just we just refer an canny edge information to restore the actual text information, and then we perform some morphological operations to combine all small components as a one big component. Okay, this is what the component of 2D and 3D. Now these are the patches, let us say patches. These patches are going to the deep learning network, because I think you know very well. So deep learning architecture give a very good results when you pass the raw image as input. So if you just pass any feature extraction, I don't think you get a good result. Yeah, maybe, I don't know, maybe it's because of an underfitting, overfitting, and or maybe I don't know, because that one is actually, yeah, there are so many million parameters are there, but just if you give an input, feature extract features as input or just small vector, I don't think it will fit into the data, because this is very million parameters and billion parameters in the parameters. How you can tune the parameters unless you have in a large number of features and large number of data. So I think that somewhere else underfitting or overfitting issues are there. So anyway, that is the reason we don't get a good results with the deep learning when you pass, when you feed just features as input. So yeah, that we know very well, that is a known fact. So that is the reason what we did actually. We try to restore the patches. Don't give any just features or something or small things now. So try to give any patches input for deep learning. Okay, that is the concept here. So now these are the actually patches now. This is the architecture we proposed. I think you was saying that some kernel based or something you was saying. I don't know actually how it works and what is this one. So anyway, input is the patches now. For each patch, yes, you're doing so many things inside. So that means you're convolving many layers and many ways of extracting the features, and finally output is yeah, this one. So output is, of course, you are getting some map like this. So then finally they fix some threshold. So to get an exact, it's some kind of a threshold, yeah. So when they get a probability map like this, of course, so now we can see high information for this. Anyway, you can see, we can see easily separate what is background and what is the foreground or what is the text information which is highlighted here. So of course, fixing threshold is not a problem. So they will try to fix a threshold to get this information now. So now you separated this information. So this is output of deep learning now. So it is a combined now. So we used in feature extraction also. So using feature extraction, we got some candidate points. From the candidate points, again, we fed in candidate points to deep learning to get this information. Okay. Now B-spline fitting. That's what an adaptive B-spline. So now this is actually the control. So now we are going with a perpendicular to this direction. So we are, until we reach this point, there's a boundary point. So we call these are all control points. So of course, that is what the input for B-spline fitting. So we just pass these control points as B-spline automatically it will fit in we'll get a smooth curve. Okay. So that means the point is this one. If it is a horizontal line, then no problem. If it is arbitrary line, then it will be a problem. Of course, in case of arbitrary line, every character is rotated in different direction. And in our 3D, not only rotated, it can be decorated character here. That is a problem here. So that means every character can have not only shape changes, some decoration also. That is the reason it is not so easy to fix a bounding box. If you just take in a global information, it is not sufficient, because every character is something different. You need something information about the character itself. So that is the reason we are going for the many local points, local control points here. So control points, so according to the control points, of course, this is a, yeah, like a character or some components here. From the components we are getting perpendicular, we traverse in perpendicular until we reach in boundary points like this. So then finally, yeah, from the control points we fix this bounding box. Okay. um, yeah, I think that's the base spline fitting. Then this is the final output. You see, any direction, no problem. Okay. So this one still it is a problem actually. ACSC, the bounding box is not exactly the tight bounding box. It covers some background information. Yes, that should be removed. That is what in the next our thinking. So how we can remove this information. So of course it's not so easy. And yes, if it is a simple line, horizontal line, then no problem, we can fix a bounding box easily. But if it is something curved in this way, it is not so easy. Okay. Yeah, that's all the contribution here. You see, look at this is IEEE transaction paper. So GGBF we proposed, wavefront concept we proposed, and adaptive B-spline splitting we proposed. It is a combination of deep learning and handcrafted features. Okay. Okay, sorry. Now, of course, these are all data set only. Just you go with results, sample images of each data set. This is our video, and this is a 2D. This is a 2D our video, and this is standard data set. These are all we have used in some standard data set for experimentation. Yeah, this is again ablation study. See, proposed with only GGVF, proposed with conventional GVF, proposed with only wavefront, proposed without GGVF and wavefront, proposed conventional polygon fitting, proposed without yeast and tesseract. Of course, I forgot to explain this one. So we use an yeast method and recognition tesseract result for eliminating false positive. So though we used in a wavefront concept and this concept and adaptive spline everything, but finally, for some of the images, especially complex background images, we are getting some false positives. So to remove false positive, what we did here, so we used a combination of an yeast. Yeast is actually text detection method. Tesseract, I think you know very well. This is a detection recognition OCR. So we just use yeast and tesseract for to remove false positives. Okay, because say OCR, if it is a text, you will get in some recognition result. If it is non-text, then how OCR, what OCR gives? Nothing, some garbage, some null values. Okay, so that one we're trying to use, because if there is a text means OCR should give a proper recognition result. Okay, so that is the one step we used here. So we are trying to show what is the effect of this step, and proposed with individual frames. Even as I mentioned, so if you take an individual frame, what happens? So of course, average frame, that's what for us, what is the input? Average frame as input now. So if you just take an individual frame, yeah, see, look at the accuracy now. So average frame is definitely a good result for this one. It's improved result. Okay. Yeah, this is ablation study. And of course, these are all the standard data set, total text. There are many standard data set are there. And these are the methods available. Just we have compared with the proposed method. I think proposed method is better than existing methods, even for this actually 2D text, not actually scene text, not actually video text. Our data set actually video text. This is existing methods, yeah, 2D text, not 3D text. So some limitation, yes, this is a limitation of, of course, definitely not so easy to solve the problem. So yeah, sometimes you see text over text. So yeah, there is a text, but within that you can see some other text. So we miss this information. It's not so easy. And text and background. So something, camouflaging. So text match with the background. So definitely we cannot solve the problem. It's not so easy. Then of course we need to go for the context information. So then in that case, we are trying to think, maybe we can bring in a natural language processing here. So then it will be, yeah, we can solve the problem. Maybe assume that this is a one box, this is a one box. How we can say this is a background? How we can say this text information? Of course, text always gives in some meaning, right? So yeah, maybe we can bring in a natural language processing here. So NLP here. So NLP automatically gives in a meaning. Something is not giving meaning, yes, it should be non-text. Something which is giving meaning, it should be text. Doesn't matter whether it is a background is same or something, because you're going with the context, you're going with the meaning information. So that is where maybe I think that's improved. Next, our extension. So we are trying to expand even wavefront also. We are trying to bring in a natural language processing also, or maybe we can think of an evolution genetic algorithm also. So when you have a more points, how we can get, instead of a wavefront concept, maybe we are trying to remove wavefront concept with a what is this one, genetic algorithm. That's what also we are planning, because genetic algorithm, you know very well, when you combine good and you are getting good, when you combine bad, you are getting a bad. So that is a concept we are trying to bring here. So when you have a many paths and many ways, then how we can choose the best path. So yes, the best we cannot choose simply. Yes, in this approach we have used an interpolation technique and a cost function, weight information according to the wavefront concept. So yes, instead of that, maybe we can replace the whole wavefront concept by genetic algorithm. So of course, you can estimate the tentative values. After getting the tentative values, bring in a genetic algorithm to find the best tentative value, not in all the values. Not just avoid weight, cost function, something like this. So that's all. Maybe probably yes, we can improvement of this method. I think, yeah, no need to explain conclusion and future work. That's the one. That's a future work I already explained. So just look at this paper. Yeah, it is just modified now and submitted back to the journal. These are all actually modification yellow color text. Yeah, it's the same thing I presented here. Yeah, maybe we can look at some equations here. Even the generalized GGVF also, it is not so easy. Yes, actually we have approached, we have taken help from the signal processing guy who he actually helped us to derive modification. He helped us to modify the conventional GGVF. So then yes, these are all equations for, yeah, wavefront concept. Yeah, I think that's it. Yeah, this is a deep learning concept. Yes. Yeah, that's all video text reduction. Anyway, I think we have some time. Probably we can go to another topic. Just I will go with this one. I'll just introduce. Not taking too much time. Maybe they can. I don't know how much time they can give. Now it's around 2:50 here. 2:50 means maybe another half an hour. Yeah, maximum half an hour, or yeah, maybe anyway. Maybe let them tell. Let them ask me to stop. No problem. I'll just start this work and see. Anyway, I will not explain in detail. Just I'm trying to highlight here. So how we can extend our problem. Okay, how we can find a new applications and new challenges so that we can survive, we can sustain in the same field and the same problem, same field. So let us say video text reduction is a one field or one area. Then how we can continue with the same field and same area. So rather than changing different areas and different problems. So yeah, some people go in that way, but some people don't like that way also. So anyway, here I'm trying to explain how we can find new applications and new problem so that we can continue the same topic as your research topic. Okay, just I will not take too much time here because no need to explain so many things here because it's not important for you now, today's session. So yeah, this is actually, yeah, text reduction. I don't want to give anything now, just right away. No need to show any papers also. See, initially let us say video text reduction, it is horizontal text reduction. So horizontal is simple now because it's not multi-oriented. See, now the next challenge is actually multi-oriented. That should be another problem now. So if you want to address this multi-oriented text reduction, this again you need to propose something new algorithm or new method now. So as I mentioned earlier, arbitrary text. See, just to handle the problems of an arbitrary text. So we proposed B-spline fitting curve. So like this, we have to, if it is a multi-oriented, then it is very difficult for you to fix the bounding box, even detection also. So that is the reason. So now there is a scope for improvement. There is a scope for contributing your your method, contribution. Okay. Yes, applications, no need to explain, no need to go. Just straight away. See, this is another problem now. Arbitrarily oriented text reduction in video. See, initially simple text reduction horizontal, multi-oriented. So that means multi-oriented means it should be in one angle. It's oriented, but it should be in one angle. Arbitrary oriented, yes, every character will have a different angle. Okay, arbitrary means every character will have a different angle. So our multi-oriented is just in one straight. Okay, it can be, yes, one line can have a different angle, but all characters will have same angle. Okay, that's arbitrary. See, this is the complexity increases now. When complexity increases, then of course simply we cannot use existing method, or simply we cannot use any simple method. So you need to, yes, there are some challenges now. We need to bring the new concept or new methodology here. So that is where there is a scope for contribution here. Okay, so yeah, then okay, this is again arbitrary. This is low light images now. See how I am changing the problem now, how I am increasing the complexity now. So text reduction topic is same, but now I am focusing on low light images now. So that means yeah, low light, of course we are losing brightness here. When image loses brightness and sharpness, then how we can see edge information? Without edge information, I think no algorithm will work. You take any image processing, probably, generally, yeah, you take any image processing algorithm or any method, without edge, no, because edge information is important information in the image. Because of the edges only we can see something, we can read something, we can find some shape, we can, yeah, that is what any edge. Without edge it should be plain background only, plain, nothing will be there. Okay, so now, so light, low light images means it will be dim light. Okay, so it's very difficult for you to now, because you image lost in sharpness and edge brightness now. So how we can enhance it? Okay, there are many ways. One way is enhancing the image, and another way is you develop a robust method which can detect even it is a image is a image is a low contrast, and image does not have high sharp values. Okay, that is the one thing. How we can solve, I think we have already solved this problem, we already published a paper also, that's what, and I don't want to show this one, it's okay. Now this is, see, text and license plate detection in a crowded street. This problem is totally different now. Low light, it is totally different now. Now it is this problem is totally different now. See, look at now, especially in India, what is happening, so many vehicles will be there now. Yes, how we can detect the license plate now? License plate is nothing but about text detection for me. How we can detect now? Because of the many vehicles and obstacles also, even the person also, even light also, street lamp also, it is really very complex problem. Why it is a complex problem? Because see, when you are capturing in images like this, the focus will be distributed into different way. That means in, see, when you have a one single plate, just your focus is on only single. That means in focus is only on single number plate. But when you have multiple plates now, focus is distributing now. Focus is scattered now. It is something like a defocused problem. It is not focused problem. It is a defocused problem now. So not only defocused, illumination problem also. Not only that one, even occlusion also. See, those are all the issues of in a crowded street on text detection in the crowded street. So this is another problem. Of course, application is also different now. So there are many challenges here. Okay, now you just try to bring something to solve this problem. Of course, we have already solved this problem. So yes, this is the one, I think, like this. Yeah, if I start showing the paper, then it will take too much time. Maybe just I will try to explain what could be the challenge and what could be the problem. Like this, it's already published now. So yeah, like this. So this is another problem now, text reduction in occluded natural scene images. See, text reduction is the same problem, but because of the tree, we are missing information here. So how we can restore the missing information? Now, yes, there is a scope for introducing NLP concept here. Now we can combine text reduction and NLP concept, because for NLP what happens? See, it's very simple. So for NLP, I think you know very well. So there is a one character, there is another character here. Middle character, always we can restore it. Even I think when you write in a Gmail or something, when you're writing one character, automatically the system will predict another character, next character. How it is possible? It is all something NLP and knowledge base, and so many things are there. So can you bring the same concept here? So detect the text information. Now assume that you missed left and right part, incomplete word now. So you're missing something in the middle information now. So you have a two parts now, part one, part two. So now with the part one, you get some information, part two, you get some information. So you combine these two information. So what should be the middle one? Of course, NLP, if you apply NLP, what is see, even NLP also see, when you're typing your character in a Gmail, so first character, when you type first character, probably it will predict another character. Exactly the same. So part one, when you're predict part one, from the part one, you are getting something, predicting something. Part two, again, you're predicting something. Of course, then you see what is the best match here. Part one is also predicting the same, part two also predicting the same. Now you see the best one. Choose the best one, should be the correct one. That's the simple. So NLP concept, actually we solved this problem. You have already submitted. I think, yeah, this is somewhere else submitted here. But no, I don't know the result. But this is a conference paper. It's already published. Yeah, this is published now. Yeah, this is again another problem now. Marathon and sports. See, this is a text marathon. Again, it is a different now. Why? Because it's not a normal text now. So here we can expect number also. Not only number, very interesting point is actually this cloth. We call actually deformable reason. So that means there will be some kind of a deformable variations. So there will be some variations in the background. So when you have a variations in the background, definitely the text becomes something different now. So, And of course you can bring in a lot of information also, you can bring in new concepts also. So now people used in a face detection algorithm and a torso detection algorithm, leg information. So then finally, yeah, torso is nothing but what this is a torso now. So get the torso and then get the text information. So this is a torso, and after getting the torso information, yes, you are getting the text. Then torso as input for the text detection. So like this, they combined in a multimodal method also they proposed. So, but of course, this approach is this problem is really challenging now. Why? Because of the cloth, because of the short text information. It is short, not like in one line like this. Most of the time, you get in words only, and sometimes even numerals also. And sports and marathon, yeah, even single digit also. When you have a single digit, how we can apply a deep learning method? It is not so easy. Okay, because deep learning or maybe yeah, if you want to achieve better results, you need some context information. So without context, at least if word contains some few characters, then yes, we can get some information. Otherwise, just single character, single digit. How we can say that this is a character? You need some extra information. You need diver information to confirm is a text. It is a digit. Okay. So that is another problem with marathon and sports. How we can solve the problem? Yes. Just actually we have solved somewhere else. Yeah, we have solved this problem. Yeah, this is a PR is already published now. Yeah, marathon runners and sports player. So next, multiple use. This again, now we can bring a concept of an fusion also. That means, as I mentioned in the beginning, I think the spot is same spot, but you are capturing in different angle, different views. Okay, one from left side, one from right side, one from top, one from like this. But same spot, but you are capturing a different way. So we can just define it as a multi-view problem. So when you have a multi-view, definitely now you just try to fuse, bring in a fusion concept now. How we can, okay, there is some information here, there is some information here, there is some information here. How we can fuse the information so that you will have a better result now or better information now. This is actually sports, especially when you go to the sports, what happens? So assume that if you want to trace the guy, if you want to track the guy or trace the guy, this sports section is a big auditorium will be there. There will be many cameras will be there. So when this guy is moving towards that camera, it will be zoom in, zoom out, and this it looks like a big font or big image. Then if he's away from the uh, that camera, then it looks very small. So one camera captures a big, another camera captures small. So different angle, different views also. So for same spot, you are getting in so many views now. Of course, I'm just showing in three views here. There will be many multiple views. So when you have a multiple views, then how you can fuse the information, because information is common in all the views. That's what an advantage for us. We know that there is a common information in all the views. Now, how you can? So this is really very good problem, and of course, definitely we can solve many problems here. Occlusion also we can solve, blurring effect also we can solve, perspective distortion also we can solve, because in one image it looks very good, in another image it doesn't look any good. So you just choose now, okay, in which image it looks good now. You take it, but how? It is not so easy. Okay, so that is where this problem. Of course, we have solved this problem. Um, so yes, it's already published now. So of course we have considered only two views now. So extension of this method is multiple views. So not just two views, we are going with the four views and more than four views. Okay, left, right, top, and back, like this. One, two, three, four views. Okay, even different angles also. We are varying different angles. We are varying the distance also. When you are changing the distance, again you are getting some views also. Like this, we are trying to capture in different ways so that we get in a lot of information. Then we are trying to um, merge or trying to fuse the information. So that's what we are thinking. That should be the extension of this work. And this is on drone images now. This is now is very quite common in very common in Malaysia. So Malaysia, our plan is actually, because I am consultant of the one of the company funded by Malaysian government, license plate detection and recognition. Actually, I'm because of the consultant only I got this problem. See, now our problem is something like this. So especially in parking, in Malaysia, yeah, car parking is really problem. So small car, big car, and of course there will be even very big in car parking. So very huge areas will be there. So it's actually open car parking. So so they have to identify illegal car parking, because in parking itself, and people, even though there is no space for the car park, they will try to park it some some way. They will find in this corner, that corner. Okay, corner some space will be there. Oh, they will park it. And okay, there is a near to the door there will be some space will be there, so they will park it. So this is the problem. So that means they're trying to park in randomly. So they don't follow the parking. Of course, when it is a full, then what they do? They just park somewhere else. So that is what they do. So the drone now, our idea is something like this. Drone automatically fly over the car parking. So and finally it will send information that okay, there is a car parked illegally. But the problem is license plate detection is not so easy now, because we are capturing from this angle. And of course the distance also varies now. If it is very near the drone, then it is fine. If it is very far, and of course something in the evening, it is very difficult. And cloudy, of course we cannot fly in drones at all. So in those are the issues. So we are trying to solve this problem. Of course we have already solved in a license plate detection when you have like scattered vehicles, like in individual vehicles. When you have in a dense vehicles, then that is a problem, because when you park full, the car park is full, then it is very difficult to locate the license plate. So for that again we need to go with a different strategy and different methodology. So we are trying to think in vehicle detection first, so surface detection first. From the surface we are defining this one as a context. From the context information we are trying to locate the rear end, front end, this one. And then front end, from the front end we are trying to exact location of the license plate. Then blindly we'll choose the license plate information area, then we are sending to something to confirm that that should be the license plate. Like this, we are just going in a different way, because it is not so easy, because we are capturing from the top. Okay. So yeah, so this is yeah, we just submitted, I think. Yeah, this one is submitted. We don't know whether we get acceptance or not. So, okay. Now this is a 3D. I think just now I explained. Yeah, we have solved this problem now. So what should we do next? Okay. Yes, we cannot then keep silent. We cannot then sit. We cannot say that okay, problem is saturated. There are no problems in text reduction. No, one cannot say this. One cannot say like this. If you keep saying like this, then one day you should stop everything. There won't be anything for you. Okay, how we can survive then? Okay. So now, yes, this is another image, another problem now. So text reduction in recaptured and distorted social media images. So recaptured is nothing but a what, something like you can assume that you are recording whole movie in the movie theater. So pirated one. So definitely your recording is a pirated one. Definitely you cannot expect a high quality. So when you have a low quality like this, then how text reduction detect, how we can detect the text information properly? Yes, that is another challenge now. Okay, so distorted social media images. See, that's another challenge now. Actually we have already assigned this problem to a student, so he's working on that. So maybe our plan is to submit to ICCV. Yes, maybe March is deadline. International Conference on Computer Vision. Yes, he's working on this problem. See, distorted is actually is a very challenging problem. Social media. See, when you upload on social media, maybe Facebook, maybe Twitter, maybe Instagram, or your WhatsApp, whatever it may be, even YouTube. So when you upload something on those social media platform, so I think you know very well that whatever you upload, it will not be saved as it is, because every social media will have its own storage mechanism, saving mechanism. So that means what we expect, whatever you store, maybe for us no problem. We can see, we can watch video also, we cannot notice what is the changes in the content. But when you upload high quality, I don't think he can keep high quality videos. He will have his own compression technique. So that means they will have each social media will have its own mechanism to store the information. That means indirectly what I'm saying, that each platform, because of the mechanism, storing mechanism, different mechanism, it somewhere else affect the content of the video. So we can expect some kind of distortions here. Okay, so each platform, each social media platform creates some kind of distortions. Okay, now assume that a one video is passing through all social media platform now. So maybe simple. I can give a question now. Let us say one WhatsApp image. I think WhatsApp image we cannot. If you take a print, we cannot read at all. If you when you open WhatsApp image, okay, we can read. But when you take a print, impossible. It's a blur, completely blurred. So let us say what is happening. One image you are forwarding to your friend. Okay, we don't know what is his mobile capacity configuration and phone. Now again he is downloading and uploading again the same image. Again he will forward to another mobile, another friend. Assume that that guy doesn't have any very good mobile. See what is happening now when you pass through different mobiles, different configuration. Exactly the same thing is true with the social media also. So same video is passing through different social media, then we can expect so many changes in the content. Maybe we cannot notice, but there will be some problems. Now that is what then input for us. So that means, of course, we have already collected images from different social media. Now our idea, our target is something text reduction in distorted. I just defined distorted social media images. I don't say these are all in high quality images and normal images. I just defined social media images are distorted images. So now we started this. This should be another problem now. Okay, I think I should go fast. Yeah, this is one simple work you see. This is actually WhatsApp images. Yeah, image one, WhatsApp one, second WhatsApp, third WhatsApp, and then mobile. Yeah, not WhatsApp, mobile. F1, this is a mobile one, mobile two, mobile three, like this. You have passed. Then finally, yes, we observed that there will be some disturbance. Okay, this is a calligraphic. This is also another kind of a text. So this is also not so easy. Even I cannot understand what is happening. What is whether it is a text or what is a Chinese text or different text, even meaning also. Yes, of course, there is some way to solve this problem, because not so easy, because nobody follow particular pattern. It all depends on something like an handwriting. It depends on the artist, how he design the characters. So it's not so easy. That's also another problem. So yeah, this is another problem now. So text detection in underwater images. So of course now, yes, nobody has solved this problem. Nobody has solved this problem, but definitely this will be very challenging. Of course, if the water is transparent like this, then it is easy to detect the text information. But don't expect all the time you will have in a transparent water like this, even though inside the sea. Okay, there will be some kind of a polluted water, stagnant water. We call in a stagnant water. So when water is polluted, then it is not so easy to read even. So how we can solve the problem? That is actually we have already assigned this problem for one master student. So he's working on that. So we are trying to enhance. First, we are trying to focus on enhancement now, because of course we have taken both the transparent water like this and even polluted water also. We are trying to add mud and so many things inside. Then you see, so whether at least we can point out where there is a text. So there will be obstacles also, there will be some objects also inside. Like this, we are creating a data set. And then finally, yes, this is a one work, very interesting and not so easy. Compared to all the previous problems, it will be something different. Okay. And this is a rail pole number detection. Especially this is not for our normal train, it is actually speed bullet train. I think, yeah, even in India also now we can see electric pole. So electric pole actually gives indication of yeah, when you have some disturbance, especially cloud and raining, clouding, then there will be some disconnection in electricity. So there will be some disturbance. So actually they want to identify, okay, which pole. So actually the pole indicates electricity. Okay, this pole near to this pole, that pole, like this. So they have their own marking and their own identification. So yes, can we identify the pole number? Yeah, it's a very tough job, because pole number is just single digit will be there, double digit will be there, and it will be something rotated also, because the pole is actually cylindrical shape. Of course, yeah, that is a problem here. And of course, most of the time, cloudy reason, because that is application now. So normal and shiny, then no issue. So yeah, there is no disturbance in electricity. Yes, when you get in, when you have in a cloudy and environment and windy, yeah, then there will be some disturbance in the electricity. In that case, yes, they want to identify, yes, where is that pole? Okay, the number. It is not in still it's a new problem. I need to find in a student to solve this problem. Yeah, this is another problem we define now. Text reduction in on deformable reason. So like you see what is happening. This is a balloon now. I think as I mentioned earlier, also it's a cloth. Cloth is actually we defined in a deformable object. So when it is a deformable, then definitely we can expect different way of text formation. Okay, cloth, balloon, yeah, like this in a traffic police identification also we can use, and cloth information, especially balloon, plastic also, rubber also, banner also, like this. That is also actually another problem. So I think we have assigned this problem for one master student again. So he's working on that. So deformable. So there are many approaches for deformable object detection. So we are trying to bring the same thing here. So instead of object, maybe we can say that as a text now. So that is what when we started now. Okay. So this is another interesting problem. It's not so easy. Yeah, maybe Indians. Yeah, we know very well that Mehndi. Yeah, in Mehndi also. Yeah, I have seen they try to write names, maybe bride or groom or something, and I remember. So it's because it's all in a camouflage. It's an overlap with decoration and design, and not so easy. That's a Mehndi is a one kind of a tattoo. Now my focus is text reduction in the tattoo images. This is actually new work. We are trying to give this problem for PhD. Let us see how. Even I don't know how to solve the problem. Just I'm thinking. Okay, this should be just recently we have identified and we found one student also. So yeah, it is a really tough job for me. It is like in handwriting also sometimes. Sometimes a lot of designs also, and of course one thing is common here, the skin. That is what I'm thinking now. Can we do something to identify the skin first, like in a cloth, like in a cloth region, like in a skin region? So there are many skin detection algorithms are there. Maybe we should think in that way. So skin detection, let us go with the skin detection algorithm and explore skin detection algorithm to find a skin first. Okay, then skin region as input for text reduction. Maybe that should be the one way of thinking the problem. Let us see how we can solve the problem. Yeah, I think those are all. Yeah, this is a one more challenge, like an ice classification, because this is a one industrial problem. So ice thickness, when a power cable is covered by ice, then there will be a breakdown. So that's a problem. And this is a one more problem is there. So it's also a totally new problem. So can we estimate a whole body from the face, or from the body can we estimate the face information, generate a face information? This nobody has solved the problem. I think deep learning can solve this problem. That is what I'm expecting also. And yes, gender identification, age estimation using handwriting analysis, nationality identification using handwriting analysis. This also we have done some work. And yes, our India also, can we see is a Kannadiga, is in Tamil and Keralian, like this. By looking at his handwriting, of course, we take in English as handwriting here, not in a script. Okay, so the guy should have in a mother tongue, yeah, his own language. Then he should write in English. Then yes, that's what an idea. And descriptive answer evaluation, forged document identification. That's also one work we are doing. And this is actually forensic application. This is actually very good and very complex problem. Photographer identification, how we identify the writer identification in handwriting. So the person signature verification, signature identification. That means, yeah, when you write something automatically, yeah, there are methods to identify, yes, who's this handwriting. So like this photographer identification, that means by looking at a photo, we should be able to tell, yes, who captured this photo, who captured. This is actually crime application, because nowadays see, wow, yes, many people capture many photos and upload on social media. Yeah, there are a lot of issues and a lot of problems are there. So uploading person is different and capturing images, yeah, that guy is different. So now how we can find, how we can trace the guy who uploaded and who captured these images? That's it's a very interesting application, but it's a very challenging problem. It is not so easy. Actually, we submitted this work, but we got rejection. Now we submitted this work to TIP. Let us see what happens. So this is a handwriting. So handwriting, forged handwriting, not like in actually nice and blur environment. That's what in our work. So we have actually, this is a major revision. We got major revision. So we have submitted back. Let us see what happens. Deep conformable moments for altered handwriting detection. That means here what we did, maybe just look at the images now. There is a normal, there is altered image, noise and blurred images. That means we are trying to detect the forged text detection, altered or forged handwriting in the blur and noise environment. I'll not go in detail what is the problem and what is the complexity here, because yeah, that maybe requires more time for you. So yeah, this is another problem. It's industry problem, tower and tower height and tower, because they need to identify automatically the problem with this tower. So if there is any defect in the tower, then the drone should go there to identify the defect. So once we know the defect, then we can send the guy to repair that one. That is what an whole is actually industry problem. Not so easy problem, because how we can say there is a defect. So because they give in drones capture in a whole area, then we receive videos captured by drones as input. Then our job is to detect, first segment the tower. After segmenting the tower, then you should see where is the defect now. Of course, they have given a ground truth also. They have a structure, proper structure is there. So we are trying to compare structure with this one. Point to point, we need to compare, and then finally we have to say that this is a defect. This is a very challenging problem. So because drone captures in different angle, segmentation itself a problem because tower segmentation and then height estimation. This is another palm tree. Actually, Malaysia palm tree is a very big business. This is the main income and the main source of income. So the problem is actually manpower, labors here. So they will have in a big and lot of acres will be there. Hectares, yeah, they say hectares now. So automatically we need to identify whether it is a healthy palm tree, young tree, mature tree. That is really not so easy because palm tree look like a coconut also, banana tree also. Even you can see mixed plants also. Some other tree will still be there. So now our job is to identify the palm tree first, segment the palm tree, then disease or maybe it is a healthy tree or not. So not so easy. Mm, yeah, we have done some work on this one. Okay, we already submitted to somewhere else. Okay. Yeah, anyway, I think that's all. These are all just sample applications. Yeah, maybe, yeah, that's all from my side.
Thank you, sir. We have some questions, sir.
Yeah.
Sir, one of the participants have asked, can you suggest any resources to study about ablation?
Hey, no, not resources. Ovulation is nothing but a word. It is actually the word. It is a word. It is a technical word. Ovulation study. It is not something in a topic and concept here. Ovulation means what? You are trying to show. You are trying to prove that the step you proposed in the methodology section is effective or not. Because whole see, when you propose in a methodology will have sub small steps will be there, right? It is one method in which you can see different steps will be there. Not just one method means it's not just in one component, right? So you will have many steps will be there. So when you have many steps, you need to prove that okay, each step is effective, each step is contributing or not. That is what an evaluation. Initially, I think, see, this is a recent word we found now. Earlier, actually, we used to say key parameters, key steps, something we used to you used in word. Okay, key analyzing key steps of the method, analyzing vital and yeah, steps of the method, like this. Earlier actually we used to do experiments, okay, individual steps to show that okay whether this contribute or not. Now they just found in one new word, evaluation study. Actually this is, I think, taken from the medical word. So you are ignoring something, doing something, you are ignoring and doing, applying something, like this. No, evaluation study is just concept. Maybe just do one thing. My suggestion is when he open any CVP or ICCV papers, a recent, any recent paper, 2020 paper, definitely that paper must have an ablation study, because that is a quite common now. When you submit a paper, immediately the reviewer or will ask this question: where is ablation study in your work? So I know very well that you just open any recent paper, there will be one section ablation study. Then yeah, just go through. So what do you mean by ablation? Ablation is just an individual step.
Okay, sir.
Hmm.
So, another question? What are
Hmm.
the expectations for a paper to get published in the reputed journal in the
Uh,
context of number of comparisons to be done and the metric of comparisons and performance for edge detection?
Okay. This is not simple question. It's a very long question, I can say. See, for compared study, yes, of course, you must have a compared study. Without compared study, it is impossible for you to publish not necessarily IEEE transactions in a top journal. Even we cannot publish in a simple conference nowadays, because nowadays is very competitive now. So even for same problem, we can see a lot of people are working on the same problem, many competitors. Every day you can see different work and different publications. So in that sense, what I am saying, so compared studies must. Why we have to go with a compared study? Why you have to have a compared study? Because you need to prove that proposed method is something different from existing methods. How we can prove that? Okay, literature survey, you are referring so many things, but that is okay just in a referring, but you are not showing in a statistically or experimentally, yes, this method has some drawbacks. So we need to show that this method is better than existing method. Otherwise nobody believe your method, nobody confirm that your method is useful. So comparison is must. Yes, true. Now the question is how many methods we should choose for comparison. Yes, this is a really question. There is no proper answer under something in a standard measure to choose okay these many methods. But generally, what we do, our experience. So in our experience, we don't go with this too many methods. Not necessary. Of course, maybe we can choose 2020. There are many papers in 2020. Yes, go with the 2020 papers only. No need to go for 2019 paper. 18, 19 not necessary. You don't have even assume that a single paper is available in 2020. Yes, take it. 2019, yes, there are two papers. You take it. Like this, maybe probably if you come to when you choose in a number of years, not more than 3 4 years. Because 2018 17 now I think that's what I'm telling. Nowadays you can see every day new method, new this one. No need to compare with an old method. Not necessary. Just compare with the 2020 or 19. How many methods? I think it's not very important. How many comparison? Not very important. What is important? Latest is very important. Of course, comparison depends on your work. How? I tell you. See, if you want to compare only concept, that will be different. So only problem or complexity of the problem. Like this, of course, if you have some divisions, then it will be different. So I'm not talking about any division, subdivision, subtask, or something like this. What I'm telling general. Okay, if there is a method now, there is a one objective now. For one objective, there should be one comparative study now. No need to go for a too many years and in a old, previous years. Not necessary. Just go with the latest method. Not more than 3 to 4 comparison. So two or three more than enough. Why? Because when you compare with the latest method, it is understood that this guy is already compared previous methods. Then what is the use of comparing again old method? And of course, it is very simple. You just ask your question only. See, young, you cannot compare with a youngster with an old man, right? And of course, higher end vehicle and lower end vehicle. How? Exactly the same thing. So comparison should be fair enough. Okay. Yeah.
Okay. Okay, sir.
Edge detection actually it's a pre-processing step. It is not something like in a classification or recognition or detection step. It is a pre-processing step. So generally, edge detection people, since it is a pre-processing, you have to go with quality measures. So not precision and recall. Precision and recall measure we use this one for retrieval, detection, recognition, classification, not for in a pre-processing step. Because edge detection means you are trying to enhance the information. So there are edges now. So when there are edges means there should be some quality. There should be some information in the information and something is preserved. So now in this case maybe quality measures, that is a one, or maybe so that is a one first step. Maybe you should go with the quality measures to confirm that yes, images are edges are enhanced. So quality measures first. So you are confirming yes there is a quality now. After confirming a quality, then probably we can go for if you just choose any application. Okay, classification, detection, recognition application. Let us say some object is there. So yes, object edges of objects are enhanced now. So if shape is preserved, shape is restored, then we can go for a detection and recognition now. We can show that now. Okay, before edge detection, yes, this is the accuracy, detection accuracy, or classification accuracy, or recognition accuracy. After edge detection, yes, this is accuracy. That is actually we call validation experiment. Like in what I did in the classification, before classification, after classification, like in before edge detection, after edge detection. Of course, for you actual measures are quality measures. So there are two kinds of quality measures again. So MSc is there, PSNR is there, and yeah, PSNR, MSc, and SSIM is there. These quality measures are very common, and these measures requires a ground truth also. If you don't have a ground truth, because ground truth means of course yeah, actual information. If you don't have a actual information, then I think there are some measures, quality measures, non-parametric. Brisk is there, NIQE is there, PIQE. There are some non-parametric measures are there. So for those measures, you don't have to have ground truth. Just you are passing your image, automatically it gives any values. Low values indicates an high quality, brisk and this one. But this one MSc, yes, error. That is error means it should be low. PSNR, it is a noise ratio, it should be high. SSIM, again, it should be high value. Yeah, I think now it's okay.
Yes, sir. So another question, can you highlight on implementation softwares for 2D and 3D text detection and classifiers?
You can use any software. I think my student used Python, because if you want to use in a deep learning, I think nowadays Python is only the solution, because Python supports for many inbuilt functions and so many things are there. Yeah, but I am not in good in those things. But for research, we don't mind, we don't care what method you use. what platform he use, what software he use, what tool he use. No, we don't care, we don't mind. Just we want what we want, okay, whether we he can solve the problem or not. So platform is not important, software is not very important, logic important, idea is important, however solving is important. So of course, when you look at the paper, we don't write an implementation, right? We don't write in a Python code, we don't write in this in a MATLAB code. Nobody write. Just of course, paper is just how many pages will be there. We cannot write in everything in the paper in the paper. We have to write only important and the core concept and logic flow and some concepts only. Yeah.
Okay, sir. Sir, another last question. If you are using deep learning for classification only and intermediate layer extract features from input, what about the overall execution time?
Execution, of course, the deep learning is always time consuming, no doubt in that. But here, what we expect, since we don't consider a learning time and training time, so just we go with the testing only. Of course, look at all the papers, so nobody report in learning and training time. We just report only testing time. Testing time, I think, doesn't matter. It is a fraction of second only. It will not affect. Of course, in our case, we don't give even input image, raw image. We are giving just a feature extraction. So definitely, yes, it will not take too much time because data is small. But of course, there are many issues here because there will be a million parameters. Learning those parameters with small data is the problem. So I cannot say definitely there will be efficient and really less time or very low time. That is impossible because that model should run. So all parameters should train with the data. So definitely, since data is very small, definitely we can expect little bit less time compared to the raw image and input image.
Okay, sir. So, thank you, sir, for your wonderful session. It was a great session on text detection in 3D video images. I, on behalf of Department of Computer Science and Engineering, PACE, extend my gratitude of having you as a speaker of the session. There were a lot of takeaway from the session. I'm sure participants have got a lot of input to carry out their research work from the session. You have also highlighted on several challenging areas that our participants can take as their research topic. Thank you very much, sir.
Yeah, thank you.